Across the endless expanse of the universe, galaxies spin like celestial whirlpools, but something doesn't add up. Their stars move too fast, their edges too stable, their motion too precise to be explained by the matter we can see. According to the laws of gravity, these galaxies should be unraveling, torn apart by their own rotation. Yet they hold together, as if guided by an invisible hand. What force is at work here? What hidden structure lies beneath the surface of the universe? This strange, unseeable influence has defied explanation for decades, hinting at a deeper truth, one that could shatter everything we think we know about space, time, and the fundamental nature of reality. This phenomenon, known as the kinematic anomaly in galaxy rotation curves, has left astronomers scratching their heads for decades. But here's the catch. This anomaly is one of the strongest pieces of evidence suggesting that our universe is far stranger and more mysterious than we've ever imagined. It might be hinting at the existence of something completely invisible, something we can't see or directly measure, but that has a profound influence on everything around it. So, what exactly is going on with these galaxy rotation curves? And what might they be telling us about the true nature of the cosmos? But before we continue, subscribe to the channel. Galaxy rotation curves, essentially graphs that show how fast stars are moving at different distances from the center of a galaxy, were expected to behave in a specific way based on Newtonian mechanics and general relativity. In a typical spiral galaxy, stars closer to the center should orbit faster, and stars farther out should orbit slower. However, what astronomers observed was completely different. At the edges of galaxies, the stars were moving far too fast. This didn't make any sense using conventional physics. Something was clearly missing. At first, the concept of dark matter was proposed as a possible solution to this anomaly. Dark matter is a mysterious, invisible substance that doesn't emit light or any other form of electromagnetic radiation. It's theorized to make up about 27% of the universe's mass energy content. But is dark matter really the key to understanding these kinematic anomalies? Or could there be something else at play? The mystery deepens. One of the most important aspects of this phenomenon is that it challenges our understanding of gravity. According to Newton's law of gravitation and Einstein's theory of general relativity, the speed of a star orbiting the center of a galaxy should drop off as you move farther from the center. This is what we observe in smaller systems, like our own solar system. However, in galaxies, the stars at the outer edges were behaving as if the mass in the galaxy extended far beyond where we could see it, which suggests the presence of some invisible mass. In this essay, we will dive deep into this anomaly and explore its implications for our understanding of the universe. From the discovery of galaxy rotation curves in the 1970s to the advent of dark matter theory and beyond, the puzzle of galaxy rotation continues to unfold, offering new insights into the workings of the cosmos. The discovery of these kinematic anomalies dates back to the early 1970s, when astronomers such as Vera Rubin and W. Kent Ford were studying the rotation of galaxies. They used a method called spectroscopy to measure the velocity of stars at different points in spiral galaxies. What they found was nothing short of astonishing. The outer stars were moving far faster than expected. In a typical spiral galaxy, the stars should move slower as you move further from the center. However, Rubin and Ford found that stars at the outermost edges of galaxies were still moving as fast as those closer to the center. This didn't match the predictions made by Newton's laws of gravitation. The outer stars were moving too quickly to be held in place by the visible matter, which led scientists to conclude that there must be some form of unseen mass exerting a gravitational influence on the stars. This invisible mass was later dubbed dark matter. But dark matter, while it might explain the rotation curves, raises a slew of new questions. For example, if dark matter makes up such a large portion of the mass of the universe, why can't we detect it directly? It doesn't emit light, and it doesn't interact with normal matter except through gravity. So, how do we even know it's there? The idea of dark matter quickly gained traction in the scientific community as the best explanation for the kinematic anomalies and galaxy rotation curves. Yet, there were other possible explanations too. Some scientists considered the possibility that our understanding of gravity might be wrong, particularly when it comes to large-scale galactic dynamics. Perhaps the laws of gravity that work well within our solar system aren't applicable on galactic scales. This notion led to the development of alternative theories of gravity. One of the leading alternative theories is modified Newtonian dynamics, MOND, proposed by Mordechai Milgram in the early 1980s. MOND suggests that Newton's laws of motion and gravity need to be modified at very low accelerations, which are typically found in the outer regions of galaxies. In this framework, the gravitational force weakens at larger distances more quickly than Newton's law predicts. This alteration could account for the high velocities observed in the outer regions of galaxies without invoking dark matter. While MOND has been able to explain some galaxy rotation curves, it doesn't fit all of them, especially when it comes to larger clusters of galaxies. The fact that MOND doesn't fully explain every case has led many astronomers to favor the dark matter hypothesis, although the debate is far from over. To better understand the mystery of galaxy rotation curves, it's important to look at how astronomers measure the velocity of stars within galaxies. The technique they use is called the Doppler effect. When a star is moving toward us, its light is shifted toward the blue end of the spectrum, while stars moving away from us produce a redshift. By measuring these shifts, astronomers can calculate the velocity of stars at different points in the galaxy. However, this method is not without its challenges. For one, it relies on the assumption that the stars within a galaxy are not moving in complex orbits. In reality, the motion of stars can be influenced by a number of factors, including the gravitational pull of other galaxies in a cluster, or the interaction between the galaxy's own stars and dark matter. These factors can complicate the interpretation of the rotation curves, making it even harder to pinpoint the exact cause of the kinematic anomalies. Another challenge in studying galaxy rotation curves is that galaxies are not isolated entities. They are often part of larger galaxy clusters, where the gravitational forces between galaxies can distort the motion of stars. This means that the rotation curves of galaxies within clusters might not be representative of galaxies that are isolated from other gravitational influences. Even though the anomalies in galaxy rotation curves are fascinating and puzzling, they have also provided a wealth of valuable information about the structure and dynamics of the universe. By studying these curves, astronomers have gained insights into the distribution of mass in galaxies, the behavior of dark matter, and even the way galaxies interact with one another. The study of galaxy rotation curves has also led to the discovery of some of the most mysterious objects in the universe. For example, some galaxies exhibit dark halos, regions of invisible matter surrounding the visible parts of the galaxy. These halos are thought to be composed of dark matter and play a crucial role in explaining the kinematic anomalies in galaxy rotation curves. But the mystery doesn't stop there. The behavior of galaxy rotation curves can also provide clues about the large-scale structure of the universe itself. Some scientists believe that by studying the distribution of galaxies and their rotation curves, we might be able to map out the overall shape and structure of the cosmos. This is particularly exciting because it suggests that the study of galaxy rotation curves could help us understand the very fabric of space and time. As we continue to explore the universe, the study of galaxy rotation curves will undoubtedly play a crucial role in uncovering some of the most fundamental mysteries of the cosmos. Whether dark matter, modified gravity theories, or some other unknown factor is responsible for the kinematic anomalies, the study of galaxies and their rotation will continue to push the boundaries of our understanding. So, what does the future hold for this field of research? One of the most exciting developments in recent years is the launch of more advanced telescopes and observational instruments. These technologies will allow astronomers to gather more precise data about galaxy rotation curves and help narrow down the possible explanations for the observed anomalies. In particular, the upcoming James Webb Space Telescope, with its unparalleled sensitivity to infrared light, could provide new insights into the structure of galaxies and the nature of dark matter. The study of galaxy rotation curves is not just a quest for understanding galaxies, it's a journey into the heart of the universe itself. It forces us to reconsider our understanding of gravity, matter, and the very laws that govern the cosmos. Each new discovery brings us one step closer to unraveling the mysteries of the universe, and who knows what we'll find next. The kinematic anomalies and galaxy rotation curves remind us that the universe is still full of surprises, and our understanding of it is far from complete. There is still so much we don't know, and every new piece of the puzzle brings us closer to a deeper understanding of the cosmos and our place within it. As we delve further into the study of galaxy rotation curves and the enigmatic kinematic anomalies that arise, it becomes clear that this is not merely a question of understanding individual galaxies. It's a question of understanding the very fabric of the universe. We are attempting to grasp the unseen forces that govern the motion of celestial objects on a cosmic scale. This endeavor is not only about finding answers but also expanding the questions themselves, pushing the boundaries of what we thought was possible in terms of our scientific knowledge. One of the most intriguing aspects of galaxy rotation curves is their connection to dark matter. For decades, the existence of dark matter has been hypothesized to explain the kinematic anomalies we observe in galaxies. Although we cannot directly detect dark matter, its presence is inferred from its gravitational effects on visible matter. The rotation curves of galaxies are perhaps the clearest and most compelling evidence for the existence of dark matter. If we look at galaxies like the Milky Way, we find that the stars and gas in the outer regions of the galaxy are moving far faster than they should based on the amount of visible matter that we can see. The gravitational force from the visible matter alone would not be enough to account for this fast motion. This discrepancy led scientists to postulate the existence of a large amount of unseen matter, dark matter, that could be exerting a gravitational influence on the stars in these galaxies. Dark matter is thought to be distributed throughout galaxies in what's known as a dark matter halo. This halo extends far beyond the visible edge of the galaxy and provides the extra mass that accounts for the faster-than-expected rotation of stars in the outer regions of galaxies. While the precise nature of dark matter remains a mystery, its gravitational influence on galaxies is one of the key factors in explaining galaxy rotation curves. However, even though dark matter is a leading explanation for the kinematic anomalies, it's not without its critics. Some scientists argue that dark matter, as we currently understand it, may not be the full story. Alternative theories of gravity, such as modified Newtonian dynamics, (MOND), have gained attention as potential explanations for the observed anomalies. MOND proposes that gravity behaves differently at very low accelerations, such as those found at the outskirts of galaxies. This modification to Newton's laws of motion could explain the rapid rotation of stars without invoking dark matter. MOND has had some success in explaining the rotation curves of galaxies, especially in the case of spiral galaxies. However, it falls short when it comes to explaining the behavior of galaxy clusters. In particular, the dynamics of galaxy clusters, where galaxies interact with one another and form large structures, are not fully explained by MOND. This is one of the key reasons why dark matter remains the more widely accepted explanation for the kinematic anomalies observed in galaxy rotation curves. Despite the success of dark matter in explaining the motion of stars and galaxies, there are still many unanswered questions. For example, if dark matter exists, why can't we detect it directly? All of the current evidence for dark matter is indirect, based on its gravitational effects on visible matter. So far, no one has been able to observe dark matter in a laboratory, and it doesn't emit any light or radiation that we can detect with current instruments. This has led some to question whether dark matter is really the right explanation or if we need to rethink our understanding of physics on cosmic scales. The search for dark matter has led to a number of ambitious experiments designed to directly detect dark matter particles. These experiments include detectors buried deep underground to shield them from cosmic radiation and other background noise, as well as experiments in space. One of the leading candidates for dark matter particles is the weakly interacting massive particle, WIMP, which, if it exists, would interact very weakly with normal matter. While experiments like these have yet to detect dark matter particles, the hunt is ongoing, and each new result brings us one step closer to understanding the true nature of this mysterious substance. But even as we search for dark matter, it's important to remember that kinematic anomalies and galaxy rotation curves aren't just about finding one solution, they're about deepening our understanding of the universe. The anomalies themselves force us to confront the limits of our current models of physics and ask whether there is more to the universe than we can see or detect. Could there be other forces or laws of physics that we have yet to discover? As we continue to investigate these anomalies, new technologies and observational techniques will play a key role in advancing our knowledge. For example, the upcoming launch of the James Webb Space Telescope, JWST, is expected to provide unprecedented views of distant galaxies and their rotation curves. With its advanced infrared capabilities, JWST will allow astronomers to observe the faintest galaxies and their structures, providing new insights into the distribution of mass within these galaxies. By comparing the rotation curves of these galaxies with current theories of gravity and dark matter, scientists hope to resolve some of the mysteries that have eluded us for so long. Additionally, advancements in computer simulations and modeling are allowing scientists to better simulate the behavior of galaxies and their rotation curves. These simulations can incorporate different types of dark matter, gravity theories, and galactic dynamics, helping researchers test various hypotheses and refine their understanding of the underlying mechanisms at play. As our computational power grows, so too does our ability to simulate the vast and complex interactions that shape the behavior of galaxies on a cosmic scale. At the same time, the search for alternative theories of gravity continues. While Mond has provided a possible explanation for the anomalies in galaxy rotation curves, it's just one of many theories that are being explored. Other alternative theories, such as scalar tensor gravity or theories involving modified general relativity, are being tested as potential explanations for the behavior of galaxies. These alternative theories are not just academic exercises. They have real implications for our understanding of the universe. If any of these theories prove to be correct, they could fundamentally change our view of gravity and the laws that govern the cosmos. As we continue to probe the mysteries of galaxy rotation curves, it's clear that we are on the cusp of a major breakthrough in our understanding of the universe. The questions raised by these kinematic anomalies are not just about the motion of stars or the nature of dark matter, they're about the very foundations of physics. Are the laws of gravity as we know them truly correct, or do they need to be modified on larger scales? Does dark matter exist, or is there a more exotic explanation waiting to be uncovered? And perhaps most intriguingly of all, what else is out there, beyond the boundaries of our current knowledge, waiting to be discovered? Ultimately, the study of galaxy rotation curves is not just an exercise in theoretical physics, it is an exploration of the unknown. Every observation, every anomaly, and every new discovery brings us closer to understanding the forces that shape the universe. And as we continue to seek answers, we are reminded that the universe is far more mysterious and complex than we can imagine. The kinematic anomalies in galaxy rotation curves are a testament to the wonders and puzzles of the universe. They challenge our understanding, inspire new ideas, and most importantly, keep us searching for deeper truths. In the end, the journey to unravel these mysteries may not only answer questions about the cosmos but also lead us to entirely new questions we haven't yet thought to ask. As we continue to explore these kinematic anomalies in galaxy rotation curves, we are confronted with an essential question: what would it mean for our understanding of the universe if we were to find that dark matter, or any other force we currently rely on, is fundamentally flawed? This is not just a question about galaxies or even our galaxy. It's about the very laws of physics themselves. Every time we come across a new anomaly, whether it's in the rotation curves of distant galaxies, or the gravitational effects on galaxy clusters, it challenges our assumptions and invites us to think in new and different ways. These anomalies are not just theoretical or academic curiosities. They hold the key to some of the most profound mysteries of the universe. The problem is, these anomalies are not isolated. They span across galaxies, galaxy clusters, and even large-scale structures of the universe. It is the consistency of these anomalies that points to something far beyond what we currently understand. If dark matter is responsible for the kinematic anomalies in galaxy rotation curves, then its properties should manifest in other ways throughout the universe, especially in galaxy clusters, which are massive and complex gravitational systems. But the puzzle is still far from solved, and this continues to motivate further research and experimentation. In particular, when we examine the dynamics of galaxy clusters, we see that their gravitational behavior seems to require more than just the mass visible through conventional methods of observation. The outer regions of galaxy clusters, much like galaxies themselves, rotate much faster than we would expect if only visible matter were present. This too points to the existence of some form of invisible mass, which is again hypothesized to be dark matter. But even here, we find inconsistencies that cannot be explained purely by the existence of dark matter. One such inconsistency arises from the behavior of the most massive galaxy clusters. In these systems, the rotation curves do not follow the typical trends we observe in smaller clusters or individual galaxies. Instead, we encounter something truly perplexing. The core of the cluster appears to be dominated by a high concentration of mass, likely dark matter, but this mass doesn't behave in the way we would expect based on current gravitational models. This leads to the question, could there be something else at work, something that interacts with dark matter in ways we have yet to understand? Many physicists have taken these anomalies as a clue that we may be misunderstanding not only dark matter, but also the fundamental nature of gravity. This is where the alternative theories of gravity, such as MOND and others, come into play. Modified Newtonian dynamics, MOND, for example, suggests that gravity behaves differently at extremely low accelerations, which are precisely the conditions found in the outskirts of galaxies and clusters. This theory has some success in explaining the flat rotation curves of galaxies without invoking dark matter. However, MOND's failure to explain the behavior of galaxy clusters, as well as some other large-scale phenomena, has led many to question whether it could be the final answer. Despite its shortcomings, MOND has opened the door to new possibilities. Its core principle, that gravity may not behave as we expect at very low accelerations, challenges the very foundations of Newtonian mechanics. It suggests that perhaps, in the deepest recesses of space, where the gravitational forces are weakest, the laws of physics we rely on may break down, requiring us to develop new theories that can better explain the strange phenomena we observe. This is the essence of scientific progress. We don't just accept the laws as they are, but constantly test and refine them. One of the areas where this search for new theories could have profound implications is in the study of galaxy formation. If the standard model of dark matter and gravity is insufficient to fully explain the observed rotation curves, we could be missing an essential aspect of how galaxies are born, evolve, and interact. The distribution of mass in a galaxy, especially in its outer reaches, plays a crucial role in its shape and behavior. Understanding the dynamics of this mass, whether it's visible or invisible, could provide a more complete picture of galaxy evolution. Moreover, the study of galaxy rotation curves and their associated anomalies also sheds light on the large-scale structure of the universe. The way galaxies interact with each other, form clusters, and even participate in cosmic superstructures like the cosmic web, is all tied to the distribution of mass and gravitational forces. If we are missing an important piece of the puzzle in understanding galaxy rotation, it could have far-reaching implications for cosmology as a whole. From the formation of the first galaxies after the Big Bang to the expansion of the universe itself, the interplay between mass, gravity, and motion is a key driver in shaping the cosmos. As we continue to analyze the rotation curves of galaxies, it's also important to note the role of observational technology in pushing the boundaries of our knowledge. With the launch of more advanced telescopes and instruments, scientists can now study galaxies at ever greater distances. Observing galaxies billions of light-years away allows us to look back in time, observing galaxies as they were in the early universe. This kind of research could help answer some of the most fundamental questions about the evolution of galaxies, dark matter, and gravity. One such example is the study of high-redshift galaxies, which are galaxies observed at a time when the universe was much younger. By analyzing the rotation curves of these distant galaxies, scientists can gain insight into how galaxies formed and evolved in the early universe. If we find that these galaxies exhibit the same kinematic anomalies as those closer to us, it could provide further evidence that the laws governing galaxy rotation are universal, and that the underlying causes of these anomalies are deeply ingrained in the fabric of the universe itself. In addition to studying distant galaxies, we are also improving our understanding of galaxy formation through simulations and computational models. These simulations attempt to recreate the conditions of the early universe and trace the development of galaxies over cosmic time. By incorporating dark matter, baryonic matter, and various theories of gravity, these models help us understand how galaxies form, how they evolve, and how their rotation curves emerge. This is a highly complex process, but with advancements in computing power, we are able to simulate galaxies with ever-increasing detail and accuracy. Another interesting development in the study of kinematic anomalies is the observation of galaxy mergers. When galaxies collide and merge, their internal dynamics are profoundly altered, which can lead to changes in their rotation curves. These mergers provide a natural laboratory for studying how the mass and gravitational influences in galaxies change over time. By analyzing the rotation curves of galaxies before, during, and after a merger, we can gain valuable insights into how galaxy structure and motion are affected by such catastrophic events. In some cases, these mergers can even lead to the formation of supermassive black holes at the centers of galaxies, adding another layer of complexity to our understanding of galactic dynamics. In the coming years, new observations and discoveries will continue to reshape our understanding of galaxy rotation curves and the kinematic anomalies that accompany them. Whether it's through new technologies, groundbreaking theories, or surprising discoveries, each new piece of the puzzle will bring us closer to unraveling the mysteries of the universe. We may be on the verge of uncovering new forces, new particles, or even new laws of physics that will fundamentally alter our view of the cosmos. This ongoing quest for knowledge highlights the importance of persistence and curiosity in science. The kinematic anomalies in galaxy rotation curves represent one of the most profound challenges in modern astrophysics, but they also offer an opportunity to expand our understanding of the universe in ways we never thought possible. Every observation, every new theory, and every breakthrough brings us closer to the truth, a truth that may not just answer old questions but create new ones, propelling us further into the unknown. As we continue to seek answers to these cosmic mysteries, one thing is certain: the universe is far more mysterious than we can imagine. Whether it's dark matter, alternative theories of gravity, or some entirely unknown phenomenon, the kinematic anomalies in galaxy rotation curves are only a glimpse into the vast complexity of the cosmos. The answers may not be easy to find, but the pursuit of these answers is what makes the study of the universe one of the most exciting and rewarding endeavors in science. As we continue to explore these anomalies, it's important to reflect on the broader context in which they exist. These kinematic anomalies in galaxy rotation curves are not isolated phenomena. They are deeply interconnected with many other mysteries in astrophysics, from the nature of dark energy to the expansion of the universe itself. The challenges presented by these anomalies offer a unique opportunity to re-examine the very fabric of our understanding of the cosmos. With each new observation, the questions grow, and with them, the complexity of the universe becomes even more apparent. One of the most intriguing aspects of galaxy rotation curves is the potential role that galactic halos play. The notion of a galactic halo, a vast region surrounding the visible portion of a galaxy, is not new. This halo is thought to be populated by dark matter, and it's this dark matter that is believed to contribute to the unexpected behavior of galaxy rotation curves. The shape and density of these halos have been the subject of much study and debate. But even with the advances in observational techniques, there are still uncertainties surrounding how exactly these halos function and how they influence galaxy dynamics. Studies have shown that the dark matter halo around a galaxy is not uniformly distributed. Instead, it follows a particular distribution, often modeled by a chord or cusp profile, depending on the assumptions made about the dark matter's behavior. Some models suggest that dark matter halos have a sharp central cusp, where the density increases toward the center of the galaxy. Other models propose that these halos have a flatter, more uniform distribution, particularly at the galactic core. Both of these models attempt to explain the discrepancies in galaxy rotation curves, but neither fully accounts for all the observations we have. When we consider the mass distribution within galaxies, it becomes clear that the behavior of both dark matter and visible matter plays a crucial role. In the outer regions of galaxies, where the visible matter is sparse, the rotation curves remain unexpectedly flat. This suggests that the galaxy's mass is not concentrated in its visible components, the stars, gas, and dust, but extends far beyond, into a halo of invisible dark matter. The precise nature of this dark matter and its interaction with visible matter remains one of the most important questions in cosmology today. Interestingly, the investigation into galactic halos has led to the development of new models of galactic formation. These models propose that galaxies may not have formed through the traditional hierarchical process of mergers and accretion. Instead, some theories suggest that galaxies could have formed within larger, pre-existing dark matter structures, which would have shaped their rotation curves in the process. This would imply that the properties of dark matter are not merely a backdrop to galaxy evolution but an active and guiding force in the formation and behavior of galaxies. In addition to the dark matter halo, another crucial component of a galaxy's mass distribution is the disk. The disk of a galaxy, composed of stars, gas, and dust, contributes significantly to the galaxy's overall rotation curve. However, in the outer reaches of the galaxy, where the visible matter thins out, we still observe flat rotation curves, indicating that the total mass is much greater than the sum of the visible matter. This discrepancy is one of the key pieces of evidence for the presence of dark matter. Yet, as we've already discussed, even dark matter fails to fully explain all the observed anomalies in galaxy rotation curves. A new avenue of exploration involves the relationship between galaxy rotation curves and the cosmic web. The cosmic web is a vast structure of interconnected galaxies, galaxy clusters, and dark matter that forms the large-scale structure of the universe. It is thought that galaxies are distributed along these vast filaments of matter, and their rotation curves may be influenced by their position within this web. The gravitational forces at play in the cosmic web could have significant effects on galaxy dynamics, potentially offering an explanation for some of the observed anomalies in rotation curves. Furthermore, the role of galaxy mergers in the evolution of galaxy rotation curves cannot be overstated. When two galaxies collide, their internal dynamics are severely disrupted. The stars, gas, and dark matter from both galaxies are scattered, leading to new patterns of rotation. These mergers can lead to the formation of elliptical galaxies, which have different rotation curve profiles than spiral galaxies. Understanding how these mergers affect galaxy rotation curves is essential for piecing together the larger picture of galactic evolution. Could it be that galaxy mergers are altering the distribution of dark matter within galaxies, causing the observed anomalies in rotation curves? Another fascinating aspect of galaxy rotation curves is their potential to provide insights into the nature of dark energy. Dark energy is the mysterious force that is driving the accelerated expansion of the universe. Its influence is most apparent on cosmological scales, but could it also have an impact on the dynamics of galaxies? Some researchers believe that the kinematic anomalies in galaxy rotation curves could be linked to the same mysterious force that governs the expansion of the universe. If this is true, it would represent one of the most profound discoveries in modern physics, as it would suggest a deep connection between the largest and smallest scales of the universe. Dark energy, in this context, could be acting as a form of repulsive force within galaxies, counteracting the gravitational pull of dark matter and visible matter. While this is a speculative idea, it is one that could potentially explain the strange behaviors we observe in galaxy rotation curves. If dark energy is influencing the dynamics of galaxies, it could provide the missing piece of the puzzle in understanding why some rotation curves deviate from what we expect. This idea ties into broader questions about the relationship between dark matter and dark energy. While dark matter is thought to contribute to the mass and gravitational pull of galaxies, dark energy is believed to be responsible for the accelerated expansion of the universe. Could these two forces, which seem to have opposite effects, be intimately connected in some way? Could the kinematic anomalies we observe in galaxy rotation curves be linked to a deeper, underlying connection between dark matter and dark energy? These are questions that will require future research to answer. As we continue to unravel the mysteries of galaxy rotation curves and the anomalies they present, we must also consider the role of observational limitations. While we have made tremendous strides in understanding galaxy dynamics, our ability to observe galaxies, especially those at great distances, is still far from perfect. The resolution of our telescopes, the sensitivity of our instruments, and the limitations of our data analysis methods all play a role in shaping our observations. As our technology improves, we may find that some of the anomalies we observe today are simply the result of observational errors or limitations. However, it is also possible that the anomalies are real and that they represent something far more profound. As we push the boundaries of observational technology and refine our methods, we may begin to uncover new insights into the nature of galaxies, dark matter, and the fundamental forces that govern the universe. The future of galaxy rotation curve research is filled with exciting possibilities, and we are only beginning to scratch the surface of what these anomalies may reveal. One of the most promising advancements in this field is the development of more advanced simulations of galaxy dynamics. These simulations allow scientists to model the behavior of galaxies under different conditions and test various hypotheses about dark matter, gravity, and other fundamental forces. By running these simulations on supercomputers, researchers can explore a wide range of possibilities and gain deeper insights into the factors that influence galaxy rotation curves. These simulations also allow scientists to test the predictions of alternative theories, such as MOND and others, in a controlled environment. The combination of observational data and computational simulations is likely to be the key to unlocking the mysteries of galaxy rotation curves. By comparing the predictions of different models with real-world observations, we can gradually refine our understanding of galactic dynamics. This process will not only help us explain the anomalies we see in galaxy rotation curves but will also shed light on the larger mysteries of the universe. As we look ahead, it's clear that the study of kinematic anomalies and galaxy rotation curves will continue to be a central focus of astrophysical research. These anomalies are more than just oddities in the data. They represent the edge of our understanding of the universe. Each new discovery brings us closer to solving some of the most profound questions in science. And while we may not have all the answers yet, the journey toward understanding these cosmic mysteries is one of the most exciting and rewarding endeavors in modern physics. As we delve deeper into the complexities of galaxy rotation curves and their associated anomalies, one must reflect on the larger implications that these discoveries might have for our understanding of fundamental physics. These anomalies have the potential to stretch beyond just the realm of astrophysics and into the very heart of theoretical physics, challenging and potentially reshaping the models we've come to rely on for describing the universe. One of the most pressing challenges posed by the anomalies in galaxy rotation curves is the apparent need for new physics. While dark matter provides a compelling explanation for many of these irregularities, it is clear that there are still gaps in our understanding of its exact properties. For instance, the hypothesis that dark matter consists of weakly interacting massive particles, WIMPs, has long been the leading theory, but this has yet to be confirmed through direct detection experiments. The failure to detect dark matter particles directly raises important questions about our current models, which rely heavily on this elusive substance. The detection of dark matter would not only resolve one of the most significant mysteries in modern physics, but could also have profound consequences for our understanding of the universe. The current models of galaxy rotation curves are based on the assumption that dark matter is distributed in a way that contributes to the gravitational pull we observe in galaxies. If this assumption turns out to be incorrect, it would require us to rethink not just the nature of dark matter, but also the very laws of gravity themselves. This brings us to the possibility that the kinematic anomalies in galaxy rotation curves could be a result of an incomplete understanding of gravity. The Standard Model of Gravity, based on Isaac Newton's laws and Albert Einstein's general theory of relativity, has been extremely successful in explaining a wide range of phenomena, from the motion of planets in our solar system to the bending of light around massive objects like black holes. However, the anomalies in galaxy rotation curves suggest that there may be factors we've yet to account for in our understanding of gravity, particularly on galactic and cosmological scales. Some alternative theories, such as modified Newtonian dynamics, MOND, propose that gravity behaves differently at the large scales of galaxies. Mond suggests that at low accelerations, like those found in the outer regions of galaxies, gravity becomes stronger than predicted by Newtonian mechanics. This would explain the flat rotation curves of galaxies without requiring the presence of dark matter. While Mond has had some success in explaining galaxy rotation curves, it remains controversial, particularly when applied to larger cosmological structures like galaxy clusters. The search for alternative gravitational theories is not just an academic exercise. It's driven by the real, pressing need to understand the universe at a deeper level. If gravity behaves differently on large scales, it could have far-reaching implications for our understanding of cosmology, from the formation of galaxies to the behavior of the universe as a whole. It could also impact our understanding of dark energy, the mysterious force responsible for the accelerated expansion of the universe. Could dark energy and the anomalies in galaxy rotation curves be two sides of the same coin, caused by a deeper, unified force of nature? This is a question that will likely guide much of the future research in astrophysics. In parallel with the search for new theories of gravity, astronomers continue to refine their observational techniques. One of the major challenges in studying galaxy rotation curves is that many of the galaxies we observe are located at vast distances, which makes accurate measurements difficult. The further away a galaxy is, the more its light is redshifted due to the expansion of the universe, making it harder to distinguish between different types of galaxies and accurately measure their rotation curves. To overcome these challenges, astronomers are developing more advanced instruments and techniques. For instance, the upcoming James Webb Space Telescope, which is set to launch in the near future, will provide unprecedented resolution and sensitivity, allowing us to observe distant galaxies in more detail than ever before. This will enable scientists to study galaxy rotation curves with greater precision, potentially providing new insights into the nature of dark matter and the forces governing galactic dynamics. In addition to improving observational tools, another avenue of exploration lies in the development of new computational models. As mentioned earlier, simulations play a crucial role in testing different hypotheses and refining our understanding of galaxy dynamics. These simulations rely on complex algorithms that take into account a wide range of factors, from the distribution of dark matter to the effects of galaxy mergers. By running these simulations on supercomputers, researchers can test different models of galaxy formation and rotation curves, allowing them to predict how galaxies should behave under various conditions. One of the most exciting aspects of this research is the potential for breakthroughs in our understanding of the role that dark matter plays in the formation of galaxies. While dark matter has been theorized to exist for decades, its precise nature remains elusive. The anomalies in galaxy rotation curves suggest that dark matter is not simply an invisible substance that fills the empty spaces between galaxies, but rather an integral component of galactic structure. Understanding the distribution and behavior of dark matter could open new doors for exploring the evolution of galaxies and even the formation of the universe itself. Furthermore, as we continue to refine our models of galaxy rotation curves, it's possible that we may discover entirely new types of galaxies that behave in ways we hadn't previously anticipated. Galaxies are incredibly diverse, and it's conceivable that the rotation curves of some galaxies could provide unexpected clues about the fundamental forces that govern them. The discovery of such galaxies would not only revolutionize our understanding of galactic dynamics but could also shed light on the nature of dark matter, gravity, and the very laws of physics. While the search for answers to the anomalies in galaxy rotation curves is ongoing, one thing is certain: we are entering an exciting era in astrophysics. The next decade promises to bring a wealth of new discoveries, driven by advancements in technology, observational techniques, and computational power. As we continue to probe the mysteries of the cosmos, we may uncover secrets that challenge our most basic assumptions about the universe. The study of galaxy rotation curves and their anomalies is about more than just understanding individual galaxies. It is about exploring the fundamental nature of the universe itself. The mysteries that lie within these cosmic structures are not just academic curiosities. They hold the key to some of the most profound questions in science. What is the true nature of dark matter? How do galaxies form and evolve? What role does gravity play in shaping the structure of the universe? These questions are at the heart of modern astrophysics, and they are questions that will shape the future of our understanding of the cosmos. As we continue to observe, theorize, and model the behavior of galaxies, we edge ever closer to unlocking the secrets of the universe. And when we do, it will be nothing short of a revolution in our understanding of the universe and our place within it. The quest to understand galaxy rotation curves and their anomalies also reveals a broader and more fundamental issue in science: the tension between observation and theory. As much as we have come to rely on theoretical models to explain the universe, it is often the anomalies, those unexpected or unexplained phenomena, that push us to expand the boundaries of our understanding. In this case, the unexpected behavior of galaxy rotation curves is forcing us to reconsider and refine not only our models of galactic dynamics but also our most cherished theories of physics. As astronomers peer deeper into space, they are not just observing galaxies, they are also observing the very laws of nature in action. These observations have the potential to expose gaps in our understanding, gaps that might be invisible if we only focused on the phenomena we already think we understand. In many ways, the study of galaxy rotation curves exemplifies the very essence of scientific inquiry, questioning, testing, and refining our ideas in the face of new evidence. It is through these anomalies that we often discover the most profound insights into the workings of the universe. Yet, despite the advancements in observation, computational modeling, and theoretical development, one of the biggest obstacles in resolving the mystery of galaxy rotation curves is the lack of direct interaction with dark matter itself. Dark matter is, by definition, invisible. It does not emit, absorb, or reflect light in a way that we can directly observe. We only know it exists because of its gravitational effects on visible matter. This means that our understanding of dark matter relies heavily on indirect evidence, such as its effect on galaxy rotation curves, gravitational lensing, and the cosmic microwave background. While these observations are compelling, they are still not direct interactions with dark matter itself, making it difficult to pin down its exact properties. This limitation in our understanding of dark matter has led to a diversity of competing hypotheses about what dark matter might be. As mentioned earlier, the most widely accepted theory is that dark matter consists of WIMPs, particles that interact only weakly with normal matter. However, alternative theories propose that dark matter could be made up of other exotic particles, such as axions, sterile neutrinos, or even primordial black holes. Each of these theories has its strengths and weaknesses, and the challenge for physicists is to determine which, if any, of these possibilities is the correct one. One approach to resolving the dark matter mystery is through particle detectors designed to detect WIMPs or other exotic particles directly. These experiments, such as the Large Hadron Collider at CERN and various underground detectors, are currently on the cutting edge of particle physics research. While these experiments have yet to provide conclusive evidence for dark matter, they continue to refine our understanding of the types of particles that could constitute it. In the coming years, new advancements in detection technology may finally provide the breakthrough that scientists have been waiting for. Another promising area of research is the study of galaxy clusters. These massive structures, which contain hundreds or even thousands of galaxies, are thought to contain large amounts of dark matter, and studying their rotation curves could provide further insights into the properties of dark matter. For instance, by observing the motion of galaxies within a cluster, astronomers can measure the gravitational influence of dark matter on the cluster's overall dynamics. In particular, the study of galaxy cluster collisions, such as the famous Bullet Cluster, has provided some of the most compelling evidence for the existence of dark matter. In these collisions, the visible matter, mostly in the form of gas, is displaced, while the dark matter remains largely unaffected, providing direct evidence of its existence. However, even with all these efforts, the question of whether dark matter is the true explanation for the anomalies in galaxy rotation curves is still open. Some researchers argue that alternative explanations, such as modifications to gravity, could account for the observed rotation curves without invoking dark matter. As we discussed earlier, the Mond theory is one such alternative, suggesting that gravity behaves differently at the low accelerations found in the outskirts of galaxies. While MOND has had some success in explaining galaxy rotation curves, it struggles to explain other cosmological observations, such as the behavior of galaxy clusters. The debate between dark matter and modified gravity is one of the most exciting and contentious in modern astrophysics, and it is likely to be a key area of research in the coming decades. As we continue to push the boundaries of our knowledge, one thing is certain: the anomalies in galaxy rotation curves are not just puzzles to be solved, they are gateways to deeper questions about the nature of the universe. Whether these anomalies point to the existence of dark matter, a modification of gravity, or some other explanation entirely, they are helping to shape the future of astrophysical research. The search for answers will undoubtedly lead to new discoveries, and each step forward will bring us closer to understanding the forces that govern the cosmos. One of the most remarkable aspects of this field of study is how it demonstrates the interconnectedness of the universe. The behavior of galaxies, from the way they rotate to the way they interact with one another, is governed by the same fundamental forces that shape the formation and evolution of the universe itself. In this way, the study of galaxy rotation curves is not just a localized problem, it's a reflection of the larger cosmic story. The anomalies we observe in galaxies could have implications for our understanding of the universe as a whole, from the birth of the first galaxies to the eventual fate of the cosmos. As scientists continue to gather data and refine their models, they are not only unraveling the mysteries of individual galaxies, they are piecing together the larger narrative of the universe's evolution. This narrative stretches from the earliest moments after the Big Bang, through the formation of galaxies and stars, to the present day, and beyond into the future. Each discovery, no matter how small, adds a new chapter to this unfolding story. In the coming years, the launch of new telescopes, both ground-based and space-based, will undoubtedly provide further insights into galaxy rotation curves and the larger cosmic picture. Instruments like the James Webb Space Telescope, which will be able to observe galaxies at unprecedented resolutions, will offer a new perspective on the rotational dynamics of galaxies, particularly those that are far away. Additionally, new observations in the radio and infrared wavelengths will help us probe the invisible structures of galaxies, potentially revealing more about the distribution of dark matter and other unseen components. Furthermore, advances in computational astrophysics are enabling scientists to simulate galaxy formation and evolution with greater accuracy. By simulating the motion of stars, gas, and dark matter, researchers can create detailed models of galaxies and test different theories about their behavior. These simulations can also help astronomers better understand the impact of galaxy mergers, supernova explosions, and other dynamic processes on the evolution of galaxies. As computational power continues to increase, these simulations will become even more sophisticated, allowing us to probe deeper into the workings of the universe. Ultimately, the study of galaxy rotation curves and their anomalies is about more than just answering a scientific question. It is about understanding our place in the universe. The mysteries that lie within these rotating cosmic structures are intricately tied to the larger questions of existence, from the origins of the universe to the fundamental nature of reality itself. As we continue to unravel these mysteries, we are not just learning about galaxies, we are learning about the forces that shape all of existence. The pursuit of understanding galaxy rotation curves and their anomalies is one of the most profound explorations in modern science. It's not simply about understanding how individual galaxies behave, but rather about grasping the true nature of the universe we live in. What we are uncovering is much more than just a cosmic puzzle. It's a journey to the very heart of physics, a journey that might one day redefine the laws that govern the cosmos. As we explore further, the key issue continues to be the role of dark matter. Its influence on galaxies, particularly in how we interpret their rotation curves, cannot be overstated. While we cannot see dark matter directly, its existence is inferred through gravitational effects. These effects reveal themselves in the way galaxies rotate, how galaxy clusters behave, and how galaxies interact with each other. But despite decades of research, the precise nature of dark matter remains elusive. This is where new theoretical models and advancements in technology can play a crucial role. The ongoing efforts to detect dark matter directly, whether through underground detectors or particle accelerators like the Large Hadron Collider, are likely to yield transformative results in the near future. If dark matter is indeed made up of weakly interacting massive particles, WIMPs, the detection of these particles would be groundbreaking. However, there are also theories that suggest it might not be WIMPs at all. Axions, sterile neutrinos, or even completely exotic dark matter candidates could provide alternative explanations. In this context, the study of galaxy rotation curves serves as a crucial laboratory for testing these theories. One area where new data is making waves is in the study of high redshift galaxies, those far away and therefore observed as they were billions of years ago. These galaxies are often in the early stages of formation, and studying their rotation curves could provide insights into how galaxies evolve over time. What's particularly intriguing about these high redshift galaxies is that many of them appear to be rotating much faster than their modern counterparts. This could suggest that galaxy formation and evolution are more complex than previously thought. The discovery of unusual rotation patterns in these distant galaxies could force us to rethink everything from the rate of galaxy formation to the interaction of dark matter with normal matter during the early stages of the universe. Beyond galaxy rotation curves, another area of interest is the behavior of galaxies in the context of large-scale structures in the universe. Galaxies don't exist in isolation. They are part of clusters, superclusters, and vast cosmic webs that stretch across the universe. These structures form under the influence of dark matter and the gravitational pull of both visible and invisible matter. The study of how galaxies move within these large-scale structures can give us important clues about the distribution and nature of dark matter. In fact, some of the most compelling evidence for dark matter comes not from individual galaxies, but from the way galaxies are clustered together and interact within their superclusters. Another way to explore the mysteries of galaxy rotation curves is through gravitational lensing. When a massive object, such as a galaxy cluster, lies between a distant galaxy and the observer, its gravitational field can bend the path of light coming from the distant galaxy, magnifying and distorting its image. This effect, known as gravitational lensing, has become a valuable tool for studying both the distribution of dark matter and the structure of the universe. By examining the lensing patterns of galaxies, we can indirectly observe the presence of dark matter and map its distribution throughout the universe. This method of investigation is revealing important insights into how dark matter behaves on the largest scales. The relationship between galaxy rotation curves and cosmic evolution is not merely academic. It is a question that has profound implications for our understanding of the future. If dark matter is indeed a critical component of galaxies, then it could also play a significant role in the ultimate fate of these galaxies. For example, the presence of dark matter could influence the process of galaxy merging and formation, ultimately shaping the structure of galaxies as they evolve. Similarly, understanding how dark matter interacts with regular matter could provide insight into how galaxies will continue to evolve in the far future. As we move forward, technological advancements will likely continue to shape the way we study galaxy rotation curves. Telescopes and detectors are becoming more sophisticated, enabling us to observe galaxies in greater detail than ever before. Instruments like the James Webb Space Telescope, which will be able to observe galaxies in the infrared spectrum, are already on the verge of revolutionizing our understanding of galaxy dynamics. These instruments will allow astronomers to study galaxies in previously inaccessible wavelengths of light, helping to further clarify the mysteries surrounding their rotation curves and the distribution of dark matter. However, the journey doesn't end with the advent of new technologies or even with the detection of dark matter. Ultimately, the anomalies in galaxy rotation curves and their connection to dark matter force us to confront deeper philosophical and existential questions about the nature of reality. If dark matter does exist, what does this mean for our understanding of the universe? How do invisible forces shape the visible cosmos? And perhaps most importantly, what does it say about the limitations of our knowledge, what we think we know versus what remains unknown? The exploration of galaxy rotation curves is also a reminder of how far science has come, and how much further we still have to go. Just a century ago, we didn't even know that galaxies existed outside of the Milky Way. Now, we are not only aware of billions of galaxies but also piecing together the invisible structure that holds them together. The discovery of dark matter, and the continuing search for it, represents one of the most profound journeys humanity has embarked upon in our quest to understand the universe. As we continue this journey, each breakthrough brings us closer to unraveling the mysteries of the cosmos. One thing is clear: the study of galaxy rotation curves is not just a scientific endeavor, it is a deeply human endeavor. It is about our innate desire to understand the world around us, to answer the questions that have puzzled us for millennia. It is about peering into the heart of the universe and asking the most fundamental questions. What is the universe made of? How did it come to be? And where is it headed? The anomalies in galaxy rotation curves, and the questions they raise, are at the forefront of this search for understanding. As we continue to explore these anomalies, we are not just investigating the behavior of distant galaxies, we are investigating the very nature of reality itself. Each new piece of evidence, each new observation, brings us one step closer to uncovering the secrets of the universe. And with each new discovery, we take another step on our journey to understand the vast, mysterious cosmos in which we live. The study of galaxy rotation curves is not just about uncovering the mysteries of the galaxies themselves. It is about unlocking the ultimate mysteries of the universe. And as we stand at the edge of this great unknown, one thing is certain: we are only just beginning to scratch the surface of what lies beyond the stars. As we continue to explore galaxy rotation curves and the anomalies they present, it becomes clear that our understanding of the cosmos is still in its early stages. Despite decades of research and advances in observational technology, there is much we still do not know. While the role of dark matter has emerged as a leading explanation for the discrepancies in galaxy rotation curves, the pursuit of knowledge in this area is far from over. Each new discovery opens up new questions, pushing the boundaries of what we thought we knew about the universe. One of the critical aspects of this ongoing exploration is the study of galaxy formation. The way galaxies form, evolve, and interact with their surroundings is intricately linked to the mysteries of dark matter. For example, the cold dark matter theory, which suggests that dark matter is composed of slow-moving particles, plays a crucial role in explaining how galaxies came to be. According to this model, dark matter clumps together under the influence of gravity, creating the gravitational wells that allow ordinary matter to fall into them and form galaxies. This process is thought to have occurred in the early universe, leading to the formation of the first galaxies. However, recent studies of galaxy rotation curves have raised some questions about the cold dark matter model. While cold dark matter remains the most widely accepted explanation for the structure of galaxies, some researchers are beginning to consider alternative theories, such as modified gravity models. These theories propose that the laws of gravity may behave differently on large scales, which could explain the observed anomalies in galaxy rotation curves without the need for dark matter. One such theory is MOND, or modified Newtonian dynamics, which alters Newton's laws of gravity at low accelerations. While MOND has had some success in explaining the rotation curves of certain galaxies, it still faces challenges in accounting for the full range of cosmic phenomena. The fact that different models can explain the same data highlights the complexity of the problem. The search for a definitive answer to the question of galaxy rotation curves and dark matter is far from straightforward. It requires not only advances in theoretical physics, but also continued refinement of our observational techniques. The introduction of new tools and technologies, such as the upcoming generation of radio telescopes and gravitational wave detectors, will undoubtedly provide fresh insights into the nature of galaxies and the forces that govern their behavior. One of the most exciting prospects for the future of galaxy rotation curve research is the potential to study galaxies in different environments. For example, the study of galaxies and galaxy clusters offers a unique opportunity to observe how galaxies interact with each other and with the larger structures of the universe. These interactions, including galaxy mergers and tidal interactions, can have significant effects on the rotation curves of galaxies. By studying these interactions in detail, we can gain a better understanding of the role that dark matter and gravity play in shaping galaxies. In addition to galaxy clusters, the study of isolated galaxies also provides valuable insights. Isolated galaxies, which are not influenced by the gravitational forces of nearby galaxies, offer a cleaner view of the intrinsic properties of galaxy rotation curves. By studying these galaxies, astronomers can better isolate the effects of dark matter and gravity, helping to refine our models of galaxy formation and evolution. Observing galaxies in different environments allows scientists to test the robustness of their models and determine whether the anomalies in galaxy rotation curves are universal or specific to certain types of galaxies. Another intriguing area of research is the investigation of galaxy rotation curves at high redshifts, which involves looking at galaxies that are far away and therefore observed as they were in the early stages of the universe. These galaxies are thought to be in the process of forming, and studying their rotation curves can provide insights into the early evolution of galaxies. Recent observations have shown that some of these high redshift galaxies have rotation curves that are quite different from those of local galaxies. This suggests that galaxy formation in the early universe may have been more complex than previously thought, with dark matter playing a more active role in shaping galaxy dynamics during this period. The discovery of these high redshift galaxies and their unusual rotation curves raises interesting questions about the role of dark matter in the early universe. Could dark matter have played a more significant role in the formation of early galaxies than we have previously thought? Or could the observed differences in rotation curves be a result of other factors, such as the interaction between galaxies and the surrounding gas? These are questions that researchers are actively working to answer, and the answers could have profound implications for our understanding of both galaxy formation and the role of dark matter in the universe. In addition to these observational efforts, advances in computational modeling are playing an increasingly important role in the study of galaxy rotation curves. With the advent of supercomputers and advanced simulation techniques, scientists can now model the behavior of galaxies and dark matter with unprecedented precision. These simulations allow researchers to test different theories of galaxy formation and evolution, including the influence of dark matter, modified gravity, and other factors. By comparing the results of these simulations with real-world data, scientists can refine their models and gain a deeper understanding of the processes that govern galaxy dynamics. These computational models also allow scientists to study galaxy rotation curves on larger scales, including the behavior of galaxy clusters and the overall distribution of dark matter in the universe. The results of these simulations can provide valuable insights into the large-scale structure of the universe, helping to improve our understanding of how galaxies are distributed across the cosmos. Additionally, these simulations can help identify regions of the universe where dark matter may be more or less concentrated, which could guide future observational efforts. As the study of galaxy rotation curves continues to evolve, the implications extend far beyond our understanding of individual galaxies. The insights gained from these studies have the potential to reshape our understanding of the universe itself. For instance, understanding the distribution of dark matter could provide new clues about the formation of the cosmos in the aftermath of the Big Bang. Dark matter is thought to have played a crucial role in the early universe, influencing the formation of large-scale structures such as galaxy clusters and superclusters. By studying how dark matter affects the behavior of galaxies, we can gain a better understanding of how the universe evolved from a nearly homogeneous state to the complex, structured cosmos we observe today. Moreover, as we refine our models of galaxy rotation curves and the role of dark matter, we may also gain new insights into the nature of gravity itself. If the anomalies in galaxy rotation curves can be explained by modified gravity rather than dark matter, it could suggest that the laws of gravity are different on large scales than we currently understand. This would represent a major shift in our understanding of physics, and could have far-reaching consequences for our theories of the universe. The study of galaxy rotation curves and the anomalies they present is one of the most exciting and important areas of modern astrophysics. The mysteries surrounding dark matter, gravity, and galaxy formation are central to our quest to understand the universe, and the search for answers continues to drive scientific research forward. As we continue to refine our observational techniques, improve our computational models, and explore new theoretical frameworks, we are moving closer to solving one of the most profound puzzles in the history of science. The insights gained from this research will not only enhance our understanding of galaxies and their dynamics, but will also provide fundamental clues about the nature of the universe itself. As we push forward into the intricacies of galaxy rotation curves and the role of dark matter, it's important to recognize the wider context in which these discoveries are taking place. The nature of galaxy rotation curves is more than just a puzzle about the structure of galaxies. It is a lens through which we can examine some of the deepest questions in cosmology and theoretical physics. While dark matter remains the most popular explanation for the observed anomalies in galaxy rotation curves, the future of this field is not just about confirming or refuting this idea. It's about testing the limits of our understanding of gravity, matter, and the evolution of the cosmos itself. One area that requires ongoing investigation is the relationship between galaxy rotation curves and the formation of the cosmic web. The cosmic web refers to the vast network of galaxy clusters, filaments, and voids that make up the large-scale structure of the universe. It's thought that dark matter, through its gravitational influence, is largely responsible for shaping this web. When we study the rotation curves of galaxies, we are also looking at the gravitational interactions that underlie the structure of the entire universe. The motions of galaxies within clusters, their interactions, and the way they are arranged within the cosmic web all speak to the ways in which gravity, driven in part by dark matter, organizes the cosmos. Additionally, galaxy rotation curves provide important insights into the nature of galaxy evolution. Over time, galaxies undergo significant changes as they collide, merge, and interact with their environment. These interactions can lead to the redistribution of both visible matter and dark matter, altering the structure and dynamics of galaxies in profound ways. For example, galaxy mergers are known to disrupt the smooth distribution of matter within a galaxy, often causing the galaxy's rotation curve to become more irregular. These mergers also provide a unique opportunity to study the role that dark matter plays in galaxy dynamics. If dark matter is distributed uniformly in galaxies, as many models suggest, it should remain relatively unaffected by these interactions, providing clues about its properties and behavior. On the other hand, if dark matter interacts in a more complex way, the effects of galaxy mergers could provide valuable insights into its fundamental nature. Furthermore, the study of galaxy rotation curves also ties into the investigation of the missing baryons problem. Baryons are the types of particles that make up ordinary matter, such as protons and neutrons. While we can detect visible baryonic matter in galaxies through various forms of radiation, there is a significant portion of baryonic matter that appears to be missing from our observations. Some researchers believe that a portion of this missing matter could be hiding in the form of diffuse gas that surrounds galaxies, gas that is too faint to detect directly. The rotation curves of galaxies can help astronomers better understand the distribution of this missing baryonic matter, particularly in the outer regions of galaxies, where it is often difficult to observe. In this sense, galaxy rotation curves may not only provide insights into dark matter but also shed light on one of the unsolved mysteries of visible matter in the universe. One of the most intriguing developments in the study of galaxy rotation curves is the growing realization that there may be regional variations in the way galaxies behave. While the standard model of galaxy rotation curve suggests a universal behavior, where the rotation curve rises steeply near the center of the galaxy and then flattens out at larger radii, this pattern may not hold true for all galaxies. In fact, some galaxies appear to exhibit rotation curves that are significantly different from the norm. These anomalies could be due to various factors, such as the presence of a large amount of dark matter, the interaction with nearby galaxies, or even the fundamental nature of gravity itself. For instance, some spiral galaxies, especially those in the outer reaches of galaxy clusters, show evidence of highly irregular rotation curves. In these galaxies, the expected flat rotation curve is either absent or interrupted by significant dips or rises in rotational velocity. These anomalies challenge our current understanding of dark matter and gravity, and may point to a need for more complex models of galaxy dynamics. In addition, the study of galaxies with irregular rotation curves may provide important clues about the impact of galaxy mergers, the distribution of dark matter, and even the interaction between visible and invisible matter in galaxies. This line of inquiry also intersects with the study of galaxy halos. The halo is a region of a galaxy that extends beyond its visible disk and contains both visible and dark matter. These halos are believed to be the dominant source of gravitational influence on galaxy rotation curves, especially at large distances from the galactic center. Observing how the halo evolves over time and interacts with the rest of the galaxy could reveal new insights into the role of dark matter in galaxy formation. The composition and structure of galaxy halos remain an area of active research, as scientists continue to explore whether the halos are made up solely of dark matter or if they also contain significant amounts of gas, dust, and other forms of matter. In the broader context of the universe, the study of galaxy rotation curves also ties into the exploration of cosmological models. Our understanding of the universe's structure and evolution is built on a framework known as the lambda-cold dark matter model, which assumes that dark matter plays a crucial role in the formation of galaxies and the growth of cosmic structures. This model provides the standard explanation for the large-scale structure of the universe, including the cosmic web, the distribution of galaxies, and the rate of expansion of the universe itself. However, recent findings regarding galaxy rotation curves, as well as other cosmic anomalies, have led some researchers to question whether the lambda-cold dark matter model needs to be revised or replaced by a new cosmological framework. One of the most compelling challenges to the lambda-cold dark matter model comes from the so-called small-scale problems. These include discrepancies between the predicted and observed number of dwarf galaxies, as well as the distribution of dark matter in galaxy halos. In particular, simulations based on the lambda-cold dark matter model suggest that dark matter should form dense, concentrated clumps in the centers of galaxies, yet observations of galaxy rotation curves show that the distribution of dark matter is often more diffuse than expected. Some researchers argue that these discrepancies point to a need for a new approach to modeling galaxy formation and dark matter. However, others suggest that the problem may be rooted in the limitations of our observational techniques, or the assumptions made in the lambda-cold dark matter framework. Another critical aspect of the galaxy rotation curve anomaly is its relationship with gravitational lensing. Gravitational lensing is the bending of light caused by the gravitational influence of massive objects, such as galaxy clusters or dark matter halos. By studying the way light bends as it passes through these objects, astronomers can infer the distribution of matter, both visible and invisible, within the lensing object. In the context of galaxy rotation curves, gravitational lensing can provide valuable information about the distribution of dark matter in and around galaxies. By comparing the lensing data with galaxy rotation curves, astronomers can refine their models of dark matter and gain a more detailed understanding of the dynamics of galaxy systems. Moreover, the observation of gravitational waves, ripples in space-time caused by the acceleration of massive objects, could also provide new insights into the behavior of galaxies and the forces that shape them. As gravitational wave detectors become more sensitive, they may allow astronomers to study the effects of galaxy mergers, black hole collisions, and other cosmic events in ways that were previously impossible. These new observational tools could complement traditional studies of galaxy rotation curves, providing a more comprehensive picture of the forces that govern the universe. Ultimately, the study of galaxy rotation curves and their anomalies is a journey into the heart of some of the most profound questions in modern science. While dark matter remains the leading explanation for the discrepancies in rotation curves, the search for answers is far from over. As our observational techniques improve, new theoretical models are proposed, and new questions arise, we continue to push the boundaries of what we know about the universe and its fundamental workings. What we learn about galaxy rotation curves today may shape our understanding of the cosmos for generations to come, helping us to unlock some of the most profound mysteries of the universe. The pursuit of understanding the anomalies in galaxy rotation curves is far from a simple academic endeavor. It is, in many ways, a reflection of our ongoing quest to understand the fundamental workings of the universe. The implications extend well beyond the study of galaxies themselves. The mysteries behind galaxy rotation curves, dark matter, and the larger forces governing galaxies may one day reshape our understanding of physics, the structure of space-time, and the nature of reality itself. As we explore these anomalies further, the question arises, could there be alternative explanations to dark matter for these peculiar rotation curves? While dark matter remains the dominant theory, there are other possibilities worth considering. One of the most intriguing alternatives is modified gravity theories, which propose that the laws of gravity might differ on cosmic scales compared to how they behave on Earth. These theories suggest that gravity may behave differently in the outer regions of galaxies, potentially explaining why rotation curves do not behave as expected. Among the most prominent modified gravity theories is modified Newtonian dynamics, MOND. MOND proposes that gravity weakens at very low accelerations, particularly in the outer regions of galaxies, which could account for the flatness of galaxy rotation curves without invoking dark matter. MOND has sparked considerable debate among physicists and cosmologists. On the one hand, MOND offers a novel and elegant solution to the rotation curve problem, providing a way to explain the anomaly using known forces. On the other hand, the theory has been criticized because it struggles to account for the large-scale structure of the universe and the gravitational lensing data that suggests the presence of dark matter. Nevertheless, MOND and similar theories continue to be the subject of intense scrutiny, with some researchers suggesting that a hybrid approach that combines elements of modified gravity and dark matter might ultimately offer a more complete solution. For instance, the theory of Tevis tensor, vector, scalar gravity extends MOND by incorporating a relativistic framework that seeks to reconcile the gravitational laws of physics with observations on both small and large scales. While these theories present intriguing possibilities, the challenge is not just in understanding the dynamics of galaxy rotation but also in reconciling these ideas with a wide range of other cosmic observations. After all, galaxy rotation curves are just one piece of the puzzle. To truly grasp the nature of dark matter, gravity, and the broader universe, we must consider all the evidence available to us, from gravitational lensing to cosmic microwave background radiation to galaxy cluster dynamics. Each new piece of information adds to our understanding of the universe and the mysterious forces that shape it. The intersection of galaxy rotation curve anomalies with gravitational lensing is particularly significant. Gravitational lensing occurs when massive objects, such as galaxy clusters or supermassive black holes, warp the fabric of spacetime and bend light passing through them. This effect is analogous to light passing through a magnifying glass, and it provides an indirect way of studying the distribution of matter within the lensing object. In the context of galaxy rotation curves, gravitational lensing can be used to map out the distribution of dark matter within galaxies and clusters, offering a new perspective on the nature of this elusive substance. One of the most exciting aspects of gravitational lensing is its ability to probe the very heart of galaxy halos, regions that are difficult to observe directly because they are often faint and diffuse. The bending of light caused by these halos can reveal the presence of dark matter and its influence on galaxy rotation. By studying how light is distorted as it passes through galaxy clusters and their halos, astronomers can create detailed maps of the dark matter distribution, helping to refine our models of galaxy rotation curves. These insights may provide critical clues about the nature of dark matter and its role in galaxy formation and evolution. Another cutting-edge area of research is the relationship between galaxy rotation curves and the cosmic microwave background (CMB) radiation. The CMB is the afterglow of the Big Bang and provides a snapshot of the universe when it was just 380,000 years old. The study of the CMB has already revealed a wealth of information about the early universe, such as the distribution of matter and energy. But recent advances in observational techniques are enabling scientists to use the CMB to probe the properties of dark matter and its influence on large-scale cosmic structures, including galaxies. By comparing the patterns observed in galaxy rotation curves with the data from the CMB, researchers can test various theories of dark matter and gravity, ultimately improving our understanding of the fundamental forces that shape the universe. It is also worth noting that the search for dark matter is not confined to the study of galaxy rotation curves alone. There are multiple ongoing efforts to directly detect dark matter particles, often through the use of highly sensitive detectors placed deep underground to shield them from cosmic radiation. These experiments, such as those conducted by the Large Underground Xenon (LUX)
collaboration, and the Axion Dark Matter Experiment, ADMEX, aim to identify the elusive particles that make up dark matter. While these experiments have yet to yield conclusive results, they represent a promising avenue for future discoveries. At the same time, advancements in high-resolution telescopes and observatories continue to enhance our ability to study galaxies and their dynamics. The James Webb Space Telescope, JWST, for example, is capable of observing the distant reaches of the universe with unprecedented detail. As JWST begins to gather more data on distant galaxies, we can expect to learn even more about their rotation curves, dark matter content, and overall structure. This new generation of space telescopes and ground-based observatories promises to open up new frontiers in the study of galaxy dynamics, providing valuable insights into some of the most profound mysteries of modern astrophysics. The exploration of galaxy rotation curves, dark matter, and the larger cosmic picture is a prime example of how scientific progress often involves solving a series of interconnected puzzles. As we work to understand the anomalies in galaxy rotation, we are also uncovering new layers of complexity in our understanding of the universe. Each new discovery brings with it new questions, and each breakthrough leads us closer to understanding the fundamental forces that govern the cosmos. In the grand scheme of things, the anomalies in galaxy rotation curves are not just problems to be solved. They are windows into the unknown, offering a glimpse into the deepest mysteries of space and time. Moreover, the study of galaxy rotation curves offers an opportunity for collaboration across multiple scientific disciplines. Astrophysicists, cosmologists, theoretical physicists, and even computer scientists working on simulations all play a role in unraveling the mysteries of galaxy dynamics. By combining observations, simulations, and theoretical models, scientists can work together to build a more comprehensive picture of how galaxies form, evolve, and behave over time. This interdisciplinary approach is crucial for advancing our understanding of the universe and solving the most complex problems in modern science. As the quest to explain galaxy rotation curves continues, it is essential to remember that these efforts are not just about filling gaps in our knowledge. They are about redefining our place in the cosmos. In understanding the forces that govern galaxies, we are also gaining a deeper appreciation for the vastness and complexity of the universe. The anomalies in galaxy rotation curves are a testament to how much there is still to learn about the universe, and how much more we will discover in the coming decades. The journey to uncover the true nature of dark matter, modified gravity, and the role of galaxy rotation curves in the larger cosmic framework is one that will likely span generations. It is a journey that may take us to the farthest reaches of space and the smallest scales of matter. As we continue to probe these anomalies, we will not only gain insight into the workings of individual galaxies, but also into the most fundamental aspects of the universe itself, leading us one step closer to understanding the forces that shape everything from the smallest particles to the largest cosmic structures. As we continue to investigate galaxy rotation curves and the mysteries surrounding them, it becomes clear that this topic sits at the intersection of several key areas of astrophysics, each contributing a vital piece to the puzzle. To truly understand why galaxy rotation curves behave the way they do, we must delve deeper into the methods used to study galaxies, explore how these anomalies might relate to other phenomena, and consider the broader implications they have for our understanding of the cosmos. One essential tool in this investigation is the study of galaxy kinematics. The velocities of stars and gas clouds within galaxies can be measured using various techniques, including spectroscopic observations. When light from these objects is split into its component wavelengths, a process known as spectroscopy, the resulting spectrum reveals subtle shifts in the light's wavelength due to the Doppler effect. This allows astronomers to determine the speed at which these objects are moving towards or away from us. By measuring these velocities at different points in a galaxy, scientists can build a rotation curve that shows how the velocity changes as a function of distance from the galactic center. For a long time, these rotation curves were assumed to follow the predictions of Newtonian dynamics, where stars further from the galactic center would orbit more slowly due to the diminishing gravitational influence of the galaxy's visible matter. However, the data has consistently shown a striking discrepancy. In most galaxies,
the rotation curves remain flat, meaning the stars at the outer edges of galaxies are moving at velocities that should be impossible if only visible matter was present. This unexpected finding is what led to the hypothesis of dark matter, an unseen, invisible substance that is thought to account for the extra mass needed to explain the high velocities at the outer edges of galaxies. The discovery of this discrepancy not only reshaped our understanding of galaxies, but also initiated a broader search for dark matter. While the idea of dark matter as an unseen form of mass has been widely accepted, the search for its exact nature remains one of the most significant challenges in modern astrophysics. Experiments aimed at detecting dark matter particles, such as weakly interacting massive particles, WIMPs, or axions, are ongoing and have yet to produce definitive results. However, the fact that galaxy rotation curves consistently point toward the existence of dark matter remains one of the strongest pieces of indirect evidence for its presence in the universe. In addition to the search for dark matter, the study of galaxy rotation curves also has important implications for our understanding of galaxy formation and evolution. It is thought that galaxies form and evolve over billions of years, with the dynamics of galaxy rotation providing crucial insights into this process. The rotation curves of galaxies are influenced by factors such as the distribution of mass within a galaxy, the interactions between galaxies, and the formation of spiral arms and other structures. By studying the detailed shape of rotation curves across a wide range of galaxies, astronomers can gain valuable clues about how galaxies assemble and evolve over time. For instance, observations of distant galaxies can help us understand how galaxy formation processes change with redshift, or the amount by which the wavelength of light from distant objects has been stretched due to the expansion of the universe. Redshift measurements are critical because they allow us to study galaxies at different stages of their evolution, giving us a snapshot of how galaxy dynamics might have looked in the past. Comparing the rotation curves of distant, high redshift galaxies with those of nearby, low redshift galaxies can reveal important differences in the way galaxies form and grow. These comparisons have led to the discovery that the mass distribution within galaxies may have evolved over time. In particular, it appears that the proportion of dark matter within galaxies might have been higher in the past, with galaxies slowly accreting visible matter over time. This suggests that the interplay between visible and dark matter is an essential aspect of galaxy formation, and the study of galaxy rotation curves could provide key insights into this process. Moreover, the shape of a galaxy's rotation curve can be influenced by interactions with other galaxies. Galaxies are not isolated entities. They frequently collide and merge with one another. These interactions can significantly alter the structure of a galaxy and its rotation curve. For example, in galaxy mergers, the redistribution of mass can lead to changes in the velocity profiles of the merging galaxies. By studying how rotation curves are altered during these interactions, we can learn more about the role of galaxy mergers in shaping the structures of galaxies and the distribution of dark matter within them. As galaxies continue to collide and merge in the distant future, the dynamics of their rotation curves will continue to evolve. However, understanding the current state of galaxy rotation curves is essential for predicting the future evolution of galaxies and the fate of structures like galaxy clusters. This is particularly important when considering the long-term fate of our own galaxy, the Milky Way, which is on a collision course with the Andromeda Galaxy. The merging of these two galaxies will undoubtedly lead to significant changes in their rotation curves and overall dynamics. Beyond the mechanics of galaxy dynamics, galaxy rotation curves have broader implications for the nature of space itself. The study of dark matter and galaxy rotation curves has led to a renewed interest in the fundamental laws of physics. The need for dark matter to explain galaxy rotation raises profound questions about our understanding of gravity and the nature of mass. Could there be a more exotic explanation for the discrepancies in rotation curves? Some scientists speculate that the laws of gravity might need to be modified on galactic scales to explain these anomalies. Modified gravity theories, such as MOND, modified Newtonian dynamics, suggest that the laws of gravity may behave differently on large scales, potentially eliminating the need for dark matter. While these alternative theories have not yet gained widespread acceptance, they provide an interesting perspective on the problem. If gravity behaves differently at the scale of galaxies, it could lead to rotation curves that appear flat, without invoking the presence of dark matter. Theoretical models of modified gravity continue to be developed and tested against observations of galaxy rotation curves. As new data becomes available, scientists will be able to assess whether these alternative theories can provide a better explanation for the observed anomalies. At the same time, the search for dark matter remains a critical part of the investigation. As mentioned earlier, dark matter is thought to make up a substantial portion of the total mass in galaxies, but its exact nature is still unknown. Many experiments are underway to detect dark matter particles directly, but so far, no conclusive evidence has been found. This is one of the most exciting aspects of contemporary astrophysics, the quest to uncover the identity of dark matter. Understanding the nature of dark matter could have profound implications not only for our understanding of galaxy rotation curves but also for the broader field of cosmology. The search for dark matter also intersects with the study of gravitational waves. These ripples in spacetime, first predicted by Albert Einstein, were detected for the first time in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO. Gravitational waves are caused by the acceleration of massive objects, such as merging black holes or neutron stars. The detection of gravitational waves opens up a new way of studying the universe, providing information about the most extreme events in space. As gravitational wave astronomy continues to develop, it could offer new insights into the nature of dark matter and the forces that govern galaxy dynamics. As we continue to probe the mysteries of galaxy rotation curves, dark matter, and the fundamental forces of nature, we are uncovering a new layer of understanding about the universe. The anomalies in galaxy rotation curves are not just a challenge, they are an invitation to rethink the laws of physics and explore the unknown. The search for answers is a journey that is still in its early stages, but each new discovery brings us one step closer to solving one of the most profound mysteries of the cosmos. Ultimately, understanding galaxy rotation curves is not just about explaining a peculiar phenomenon observed in the motion of distant stars. It is about unlocking the secrets of the universe itself, from the smallest building blocks of matter to the largest structures in the cosmos. As we continue to investigate these anomalies, we are pushing the boundaries of human knowledge, and in the process, we may discover new aspects of the universe that challenge our most fundamental assumptions about reality. As the study of galaxy rotation curves continues to evolve, new questions emerge, particularly regarding how these findings might inform the broader structure of the universe. One such question is whether galaxy rotation anomalies could lead to a rethinking of the very nature of cosmic structures. We already know that galaxies are part of much larger structures, such as galaxy clusters and superclusters, and their dynamics are influenced by the interactions and gravitational forces within these larger systems. The rotation curves of galaxies are often linked not just to their own mass but also to the influence of neighboring galaxies and the overall gravitational well of the cluster they inhabit. The interconnectedness of these systems means that galaxy rotation curves do not exist in isolation. Instead, they are influenced by a broader cosmic context, one in which dark matter plays a key role. Within galaxy clusters, for instance, galaxies are bound by gravity, and the total mass of the cluster, including the dark matter component, plays a crucial role in determining the behavior of individual galaxies. When galaxies within a cluster interact, such as during close encounters or mergers, their rotation curves can be dramatically altered, reflecting the complex gravitational dynamics at play. Thus, studying galaxy rotation curves in the context of their larger cosmic environment offers important clues about the interplay between galaxies and the dark matter that surrounds them. Furthermore, the discovery of anomalous galaxy rotation curves has profound implications for our understanding of cosmic evolution. Over the course of the universe's history, galaxies have grown, merged, and evolved, with their dynamics changing as they interact with their environments. As galaxies acquire mass, both visible and dark, their rotation curves are altered, providing a record of the processes that shape their formation and growth. By studying the rotation curves of galaxies at different stages of their evolution, astronomers can reconstruct the history of galaxy formation and the role that dark matter has played in shaping the structure of the universe. For example, studies of distant, high redshift galaxies offer a glimpse into the early stages of galaxy formation. These galaxies, which are seen as they were billions of years ago, may exhibit different rotation curves compared to more mature galaxies, reflecting the early stages of mass accumulation and dark matter accretion. By comparing these early galaxies with more evolved systems, astronomers can gain valuable insights into how galaxy dynamics have changed over time and how the distribution of dark matter within galaxies has evolved. One particularly intriguing aspect of these studies is the possibility that dark matter may have played a more significant role in the early universe than we previously thought. In the early stages of galaxy formation, the density of dark matter may have been much higher, and the gravitational influence of dark matter may have been stronger, leading to more pronounced effects on the rotation curves of galaxies. As the universe expanded and evolved, the distribution of dark matter may have become more diffuse, with the density of dark matter in the outskirts of galaxies decreasing over time. This could explain why rotation curves in modern galaxies appear flatter, as the dark matter halo surrounding the galaxy has expanded and spread out. This hypothesis could also help explain the apparent differences between galaxies with differing masses. Large, massive galaxies tend to have more extensive dark matter halos, which would explain their flat rotation curves. Smaller galaxies, on the other hand, may have less prominent dark matter halos, resulting in less pronounced anomalies in their rotation curves. The relationship between a galaxy's mass and the distribution of dark matter within it could provide critical insights into the processes of galaxy formation and the role of dark matter in shaping cosmic structures. As we probe deeper into these questions, new techniques and technologies are helping us refine our understanding of galaxy rotation curves. One of the most exciting developments in this area is the use of next-generation telescopes, such as the James Webb Space Telescope, JWST, which promises to provide unprecedented detail in the observation of distant galaxies. With its ability to peer further into the universe than ever before, the JWST is expected to offer new insights into the rotation curves of galaxies that were previously beyond our reach. By studying the light emitted by distant galaxies and measuring the velocities of their stars and gas clouds, astronomers will be able to construct more accurate and detailed rotation curves, shedding light on the mysteries of galaxy dynamics. In addition to advanced telescopes, the development of more sophisticated computational models and simulations is allowing scientists to better understand the behavior of galaxy rotation curves. These models incorporate the effects of dark matter, gas dynamics, and other factors that influence the motion of stars within galaxies. By running simulations of galaxy formation and evolution, scientists can compare the results with observational data, refining their models and testing different hypotheses about the nature of dark matter and galaxy dynamics. One such simulation is the Illustris project, a large-scale simulation of galaxy formation that models the formation of galaxies over billions of years. By simulating the behavior of dark matter, gas, and stars in a cosmological context, the Illustris project is providing valuable insights into the processes that shape galaxy dynamics. The project has produced detailed simulations of galaxy rotation curves, helping to explain how the distribution of dark matter affects the velocities of stars and galaxies. These simulations suggest that the presence of dark matter is essential for explaining the flatness of galaxy rotation curves, providing further support for the dark matter hypothesis. Yet, as we continue to refine our understanding of galaxy rotation curves, it is important to remain open to the possibility that our current models may need to be adjusted or even completely rethought. The anomalies observed in galaxy rotation curves may be signaling something deeper about the nature of the universe. Could there be other forces at work, beyond gravity and dark matter, that influence the behavior of galaxies? Some scientists are exploring the possibility that there are additional, yet to be discovered components of the universe that could provide an explanation for these anomalies. These ideas, while speculative, could one day lead to breakthroughs that completely transform our understanding of galaxy dynamics and the forces that shape the cosmos. The study of galaxy rotation curves and the kinematic anomalies they present is one of the most fascinating and complex areas of modern astrophysics. These anomalies, which have baffled astronomers for decades, are not just curiosities, they are key to unlocking some of the deepest mysteries of the universe. From the elusive nature of dark matter to the evolution of galaxies and the fundamental laws of gravity, the study of galaxy rotation curves touches on many of the most profound questions in science. As we continue to explore these anomalies, we are not just seeking answers about individual galaxies, we are seeking answers about the nature of the universe itself. The future of galaxy rotation curve research is bright, with new observational techniques, advanced simulations, and groundbreaking discoveries on the horizon. Each new piece of data brings us closer to understanding the role of dark matter in galaxy formation, the evolution of galaxies, and the fundamental forces that govern the universe. By continuing to study galaxy rotation curves, we are pushing the boundaries of human knowledge and venturing into the unknown, uncovering the secrets of the cosmos one discovery at a time. As we continue to explore the intricacies of galaxy rotation curves and the anomalies they present, one of the most exciting directions in current research is the search for alternatives to dark matter. While the dark matter hypothesis has been incredibly successful in explaining the rotation curve problem, it remains an unsolved mystery. The elusive nature of dark matter means that we have never observed it directly, and all of our knowledge about it comes from indirect evidence. This uncertainty leaves room for alternative theories that could explain the kinematic anomalies we see in galaxy rotation curves. One such alternative is the theory of modified Newtonian dynamics, MOND, proposed by Mordechai Milgram in the 1980s. MOND suggests that the laws of gravity, specifically Newton's laws, may need to be modified at very small accelerations. According to MOND, the rotation curves of galaxies do not need dark matter. Rather, the gravitational forces that govern the motion of stars within galaxies are modified at low accelerations, such as those found at the outer edges of galaxies. Under this theory, the discrepancy between the observed and predicted rotation curves could be explained by a modification to the gravitational force at large distances from the galactic center. MOND has been successful in explaining the flat rotation curves of many galaxies without invoking dark matter. It also predicts some of the observational features seen in galaxy dynamics, such as the Tully-Fisher relation, which links the rotation velocity of a galaxy to its luminosity. However, MOND is not without its challenges. It struggles to explain other phenomena that are typically attributed to dark matter, such as the cosmic microwave background radiation and the distribution of galaxy clusters. Additionally, MOND faces difficulties when applied to larger cosmic scales, where dark matter's gravitational influence plays a significant role in shaping the structure of the universe. Despite these challenges, MOND has sparked significant interest and debate within the astrophysical community. Some researchers believe that the theory may be a stepping stone toward a more complete understanding of gravity, one that incorporates both the observed phenomena at galactic scales and the behavior of matter at larger cosmological scales. Whether MOND will ultimately prove to be a viable alternative to dark matter remains to be seen, but it has undoubtedly expanded our thinking about the fundamental forces that govern the universe. Another intriguing possibility is the concept of self-interacting dark matter, SIDM. Traditional dark matter models assume that dark matter particles interact only through gravity and possibly weakly via other fundamental forces. However, in SIDM models, dark matter particles are assumed to interact with one another through additional forces, which could lead to different kinematic behaviors in galaxies. In particular, SIDM could help explain the observed anomalies in galaxy rotation curves by allowing dark matter to clump in ways that are not predicted by the standard cold dark matter (CDM) model. The idea behind SIDM is that dark matter particles, rather than being completely collisionless, interact with each other through a form of self-interaction. This interaction could cause the dark matter particles to accumulate in certain regions of a galaxy, potentially leading to a more centralized dark matter distribution. This could explain the steep inner rotation curves observed in some galaxies, which are difficult to reconcile with the predictions of CDM. SIDM models also predict that dark matter halos would be less concentrated at the outer edges of galaxies, leading to flatter rotation curves. These predictions are consistent with the observed behavior of many galaxies, making SIDM a compelling alternative to the traditional cold dark matter model. However, while SIDM offers a promising solution to the galaxy rotation curve problem, it is not without its own set of challenges. For example, it remains unclear how the self-interactions between dark matter particles would manifest in a way that is consistent with other astronomical observations, such as the behavior of galaxy clusters. Additionally, some studies suggest that SIDM may lead to over-smoothing of the structure of dark matter halos, which could conflict with the observed diversity of galactic shapes and dynamics. Further observations and simulations are needed to determine whether SIDM can provide a more accurate description of galaxy rotation curves. In parallel with these alternative theories, some researchers have focused on the role of baryonic matter, or ordinary matter, in shaping the rotation curves of galaxies. The traditional view holds that dark matter is the dominant contributor to the rotation curves of galaxies, but recent studies suggest that the distribution and behavior of baryonic matter may also play a significant role. For example, the presence of gas clouds, star formation, and supermassive black holes could all influence the dynamics of stars within a galaxy, leading to the observed anomalies in galaxy rotation curves. One area of particular interest is the relationship between star formation and galaxy rotation curves. It is well known that the distribution of stars within a galaxy is not uniform, and that galaxies can undergo significant changes in their star formation rates over time. This could have a direct impact on the rotation curves, as the distribution of stars and gas in a galaxy influences the gravitational potential that governs the motion of other objects within it. Additionally, the presence of a supermassive black hole at the center of many galaxies could also play a role in shaping the dynamics of the galaxy as a whole, including its rotation curve. The gravitational influence of the black hole, combined with the accretion of gas and the release of energy through various processes, could lead to variations in the rotation curves of galaxies, further complicating our understanding of their kinematic behavior. The complex interplay between dark matter, baryonic matter, and gravitational forces is a critical factor in understanding galaxy rotation curves. Observations of the distribution of stars, gas, and dark matter within galaxies can provide important clues about the processes that shape galaxy dynamics. By examining the effects of star formation, supermassive black holes, and other forms of baryonic matter, scientists can refine their models of galaxy evolution and gain a deeper understanding of the forces that govern the behavior of galaxies. Moreover, the role of gas dynamics in shaping galaxy rotation curves cannot be overlooked. Gas in galaxies is not uniformly distributed, and its behavior can be influenced by a variety of factors, such as the presence of magnetic fields, supernova explosions, and the interaction with other galaxies. These factors can cause gas to accumulate in certain regions of a galaxy, altering the gravitational potential and affecting the rotation curve. In some cases, gas flows may lead to the formation of spiral arms, bulges, or other features that are observed in galaxies. Understanding the dynamics of gas within galaxies is essential for building more accurate models of galaxy rotation curves and understanding the role of baryonic matter in shaping these curves. The interplay between dark matter, baryonic matter, and gas dynamics is a central theme in modern galaxy research. As we continue to study the anomalies in galaxy rotation curves, we are uncovering new insights into the complex forces that govern the behavior of galaxies. The future of this field is filled with exciting possibilities, as new technologies and observational techniques allow us to probe deeper into the dynamics of galaxies than ever before. The study of galaxy rotation curves and the kinematic anomalies they present is a rich and evolving field of research. While the dark matter hypothesis remains the most widely accepted explanation for these anomalies, alternative theories such as MOND, SIDM, and the role of baryonic matter offer compelling alternatives that could provide new insights into the fundamental forces shaping galaxies. As we continue to refine our understanding of galaxy dynamics, we are pushing the boundaries of knowledge about the universe and the forces that govern its evolution. Whether dark matter or new, unknown forces are responsible for these anomalies, one thing is clear: the study of galaxy rotation curves is essential for unlocking the deepest mysteries of the cosmos. As we move forward in our exploration of the mysteries surrounding galaxy rotation curves, another critical aspect we must examine is the growing body of observational evidence that both supports and challenges the theories surrounding dark matter and other forces in galactic dynamics. Over the past few decades, astronomical observations have become more detailed, providing a much clearer picture of the behavior of galaxies on a large scale. Advancements in telescope technology, combined with sophisticated computational simulations, have allowed scientists to study the rotation curves of galaxies with unprecedented precision. One of the most important tools for this investigation has been the study of galaxy clusters. These massive collections of galaxies serve as natural laboratories for testing theories of dark matter and gravity. Observations of galaxy clusters, such as the famous Bullet cluster, have provided key evidence for the existence of dark matter. In this case, scientists observed the separation of visible matter, in the form of gas and galaxies, from the bulk of the mass in the cluster, which was inferred from gravitational lensing. The distribution of mass in the Bullet cluster, with the majority of it being located in regions where there is no visible matter, strongly supports the idea of dark matter as the dominant form of matter in galaxy clusters. However, while these observations have been instrumental in reinforcing the dark matter hypothesis, they have also raised questions. For instance, some alternative theories, such as MOND and SIDM, suggest that the observed separation of mass could be explained by modifications to the laws of gravity or by interactions between dark matter particles themselves. This ongoing debate reflects the complexity of the phenomena we are trying to understand. Each observation brings us closer to understanding the nature of dark matter, but it also opens new questions that challenge our existing models. Furthermore, the study of galaxies that deviate from the standard rotation curve behavior has become a focal point of modern astronomy. While most galaxies exhibit flat rotation curves at large radii, some galaxies show variations that cannot easily be explained by the presence of dark matter alone. In particular, the rotation curves of some ultra-diffuse galaxies, UDGs, and galaxies in the process of merging appear to deviate from the expectations of the dark matter model. These anomalies suggest that there may be additional factors influencing the dynamics of galaxies that are not yet fully understood. Ultra-diffuse galaxies, for example, are galaxies with extremely low surface brightness and large sizes relative to their mass. Despite their apparent lack of visible matter, many of these galaxies have rotation curves that are consistent with the dark matter model, implying that a significant amount of dark matter exists in their outer regions. However, the exact distribution of dark matter in these galaxies remains a topic of active research. Some researchers propose that the observed behavior of UDGs might be explained by an overabundance of gas or other baryonic matter in the outer regions, altering the gravitational potential and leading to the observed rotation curve anomalies. Alternatively, these galaxies might provide an opportunity to explore the limits of the dark matter model itself, potentially offering clues about how dark matter behaves in low-mass systems. Similarly, galaxy mergers provide another fascinating area of study. When galaxies collide, the resulting interactions can significantly alter the distribution of both baryonic and dark matter within them. These events often lead to changes in the overall shape and behavior of the resulting system. Merging galaxies sometimes exhibit anomalous rotation curves that do not fit the predictions made by the standard dark matter model. In some cases, these anomalies might arise from the redistribution of matter within the galaxies during the collision, leading to the formation of new structures that affect the kinematics of the galaxy. The study of galaxy mergers is particularly important because it helps us understand the role of dark matter in the evolution of galaxies. The gravitational forces exerted by dark matter play a crucial role in the way galaxies interact and merge. However, the details of how dark matter behaves during these interactions remain unclear. Some researchers suggest that dark matter might be more concentrated in the centers of galaxies, while others propose that it is more evenly distributed. The study of galaxy mergers may ultimately provide the key to resolving these questions and gaining a deeper understanding of the role of dark matter in galactic dynamics. Another promising avenue of research involves the use of gravitational wave astronomy. The detection of gravitational waves has opened a new window into the study of astrophysical phenomena, including galaxy rotation curves. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as black hole mergers or neutron-star collisions. These waves carry valuable information about the distribution of mass and energy in the universe. By studying the effects of gravitational waves on the rotation curves of galaxies, astronomers may be able to gain new insights into the behavior of dark matter and other forces at play in galaxy dynamics. Recent advances in gravitational wave detection technology, such as the Laser Interferometer Gravitational Wave Observatory, LIGO, and the Virgo detector, have made it possible to detect the faintest ripples in spacetime. These discoveries have already led to groundbreaking results in the study of black holes and neutron stars. In the future, it is hoped that gravitational wave observations could provide a more direct way of probing the distribution of dark matter in galaxies, offering a new perspective on the anomalies we see in galaxy rotation curves. While gravitational waves represent a relatively new and exciting method of studying the universe, traditional electromagnetic observations, including radio, optical, and X-ray astronomy, remain essential for understanding galaxy dynamics. These observations provide the detailed, high-resolution data needed to accurately map the rotation curves of galaxies and to test the predictions made by different theories. In particular, observations of the hydrogen gas in galaxies, which emits radio waves, provide crucial information about the mass distribution within galaxies. The 21-centimeter emission line from neutral hydrogen is a key diagnostic tool in the study of galaxy rotation curves, as it allows astronomers to trace the motion of gas clouds in the outer regions of galaxies. This data is essential for understanding the role of dark matter and other forms of matter in shaping the dynamics of galaxies. In addition to radio and optical observations, the study of galaxy formation and evolution also provides valuable insights into galaxy rotation curves. The growth and development of galaxies over time is influenced by a wide range of factors, including the accretion of gas, the merger of smaller galaxies, and the formation of stars. By examining the rotation curves of galaxies at different stages of their evolution, astronomers can gain a better understanding of how galaxies evolve and how their kinematic properties change over time. This can help refine our models of galaxy formation and provide a deeper understanding of the forces that shape galaxies. As we continue to probe the mysteries of galaxy rotation curves, it is important to remember that the study of galaxies is not just about understanding the kinematics of individual systems. The behavior of galaxies on large scales is deeply connected to the overall structure and evolution of the universe. Galaxy rotation curves provide important clues about the distribution of dark matter, the nature of gravity, and the processes that govern the formation of galaxies. By continuing to study these anomalies, we are not only advancing our knowledge of individual galaxies but also uncovering fundamental truths about the universe as a whole. The study of galaxy rotation curves and the anomalies that arise from them is a critical part of modern astrophysics. Whether through the lens of dark matter, modified gravity theories, or baryonic matter, the kinematic behavior of galaxies provides a rich source of information about the fundamental forces of the universe. As observational techniques continue to improve and new theories are developed, we are likely to see a deeper understanding of these fascinating phenomena. The search for answers to the mystery of galaxy rotation curves is far from over, and the journey promises to reveal even more exciting discoveries in the years to come. As we delve deeper into the complexities of galaxy rotation curves, it's important to emphasize the broader implications these studies have on our understanding of the universe. At the core of the debate surrounding rotation curves is the question of dark matter. But beyond simply confirming its existence, we are faced with understanding its properties, its interactions, and how it influences the structure and evolution of the cosmos. The anomalies observed in galaxy rotation curves are not just theoretical puzzles to be solved, they are clues to a much larger mystery about the fundamental makeup of the universe itself. To tackle this, it's important to examine the methods used to detect and measure these rotation curves. Traditionally, astronomers have relied on optical and radio observations to study galaxies. The rotation curve of a galaxy is essentially a plot that shows how the velocity of stars, gas, and other matter within a galaxy changes as a function of distance from the galactic center. The key observation that led to the discovery of galaxy rotation curve anomalies was that, contrary to what Newtonian mechanics would predict, the outer stars of galaxies were moving much faster than expected. This discrepancy first became apparent in the 1970s, when astronomer Vera Rubin and her colleagues measured the rotation curves of spiral galaxies. According to Newton's laws, the further you move from the center of a galaxy, the slower the stars should move, due to the decreasing gravitational pull. However, Rubin found that in many galaxies, the stars on the outer edges were moving much faster than expected, suggesting there was more mass than could be accounted for by visible matter alone. This led to the inference that there must be some unseen, invisible mass, what we now refer to as dark matter. This realization fundamentally changed our view of the universe. Before this discovery, the visible matter we could observe, stars, gas, dust, was assumed to be the dominant form of mass in the universe. Dark matter, which doesn't emit light and cannot be detected directly, appended this assumption. Now, scientists believe that dark matter accounts for about 27% of the total mass and energy content of the universe, a significant amount more than ordinary, visible matter, which accounts for just 5%. However, despite the overwhelming evidence that dark matter exists, its precise nature remains one of the most elusive questions in modern astrophysics. And it is in studying galaxy rotation curves that we find some of the most tantalizing clues. The rotational velocity anomalies observed in galaxy rotation curves do not just suggest the presence of dark matter, they provide insights into the distribution of dark matter within galaxies. In many galaxies, dark matter appears to form a spherical halo surrounding the visible components of the galaxy, extending well beyond the region where stars and gas are found. The exact nature of this halo, how dark matter behaves within it, and how it influences the rotation curves of galaxies are still topics of active research. Moreover, not all galaxies fit neatly into this dark matter model. Some galaxies, particularly smaller or irregular galaxies, show rotation curves that do not seem to require the same amount of dark matter to explain their velocity profiles. In these cases, the apparent lack of a dark matter halo has led to alternative theories, including modified Newtonian dynamics, MON. MON suggests that the laws of gravity may behave differently at large scales or in low-gravity environments, offering a possible explanation for the observed rotation curves without invoking dark matter. While MON remains controversial, it has led to some intriguing predictions that continue to be tested by astronomers. Another significant aspect of galaxy rotation curves is their potential connection to the evolution of galaxies over cosmic time. Galaxies are not static objects. They evolve and change as a result of mergers, accretion of gas, and internal processes like star formation. As galaxies merge, for example, the gravitational interactions between them can cause significant changes in their rotation curves. When two galaxies collide, their dark matter halos can also interact, leading to the redistribution of dark matter and the modification of the galaxy's rotation curve. Observations of galaxy mergers, such as those between the Milky Way and smaller satellite galaxies, provide valuable insights into how the rotation curves of galaxies can change over time. Additionally, the study of galaxy formation and evolution helps to frame the broader context in which these rotation curves exist. Early in the history of the universe, galaxies were much smaller and less organized. As they grew through mergers and the accretion of gas, their rotation curves likely underwent significant changes. By studying the rotation curves of galaxies at various stages in their evolution, astronomers can trace the development of galaxies and gain a better understanding of how the properties of dark matter and gravity evolve over time. Beyond dark matter, one of the most intriguing aspects of galaxy rotation curves is the question of the distribution of mass in the outer regions of galaxies. For most galaxies, the rotation curve remains flat at large distances from the center, implying that the mass is distributed in a way that doesn't follow the expectations of visible matter alone. While dark matter is thought to be the primary contributor to this outer mass, the details of how this mass is distributed, and how it influences the overall dynamics of the galaxy, remain unclear. In fact, the shape of a galaxy's rotation curve, whether it rises sharply at first and then flattens out, or whether it stays flat from the very beginning, can tell us a lot about the galaxy's structure. Some models suggest that the mass distribution within galaxies could be more complicated than previously thought. For instance, a galaxy's central bulge or disk might influence the outer regions in ways that we don't fully understand, potentially altering the overall rotation curve. Additionally, the interaction between gas, stars, and dark matter in the outer regions of galaxies could create dynamic effects that alter the rotation curve in subtle but significant ways. One avenue that has gained attention in recent years is the study of ultra-diffuse galaxies, UDGs. These are galaxies that are large in size but have relatively low luminosity and low star formation rates. Despite their large size, UDGs have relatively shallow or flat rotation curves, which challenges our understanding of how mass is distributed within these galaxies. Some scientists have proposed that these galaxies may contain less dark matter than expected, or that their dark matter halos could be more diffuse and spread out over larger distances. Others suggest that UDGs could be the result of galaxy interactions or environmental factors that influence their dynamics in unique ways. As our observational techniques improve, these enigmatic galaxies could offer new insights into the nature of dark matter and the processes that shape galaxy rotation curves. The study of galaxy rotation curves also has profound implications for our understanding of gravity. While the presence of dark matter helps explain the anomalous rotation curves observed in galaxies, it also raises fundamental questions about how gravity operates at galactic scales. Some theories, such as MOND, challenge the conventional understanding of gravity, suggesting that the laws of motion and gravity may need to be modified at large scales. Other models propose that new particles or fields could be responsible for the observed effects. As more data is collected and new observations are made, scientists are working to refine our understanding of how gravity operates on galactic scales. The study of galaxy rotation curves and their anomalies is a cornerstone of modern astrophysics. These curves not only provide crucial insights into the nature of dark matter but also offer a unique perspective on the laws of gravity and the evolution of galaxies. As technology improves and new observational tools come online, we are likely to uncover even more mysteries hidden within the rotation curves of galaxies. Whether through the lens of dark matter, modified gravity, or other forces at play, the study of galaxy rotation curves will continue to be one of the most exciting frontiers in astrophysical research, offering new challenges and discoveries that will shape our understanding of the universe for years to come. As the study of galaxy rotation curves advances, one of the most exciting aspects is the continuous development of observational technology. With the rise of more sophisticated telescopes and observational instruments, we are now able to gather data with unprecedented resolution and accuracy. This allows us to investigate galaxy rotation curves in ways that were previously impossible, uncovering new details about the structure and composition of galaxies. One such advancement is the development of high-resolution imaging through techniques like the Very Large Telescope, VLT, and the upcoming James Webb Space Telescope, JWST. These tools enable astronomers to observe galaxies across vast distances and with incredible precision. This detailed imaging is vital in measuring the velocity of stars and gas at the outer edges of galaxies, where the anomalies in rotation curves are most noticeable. With these new instruments, we can more accurately map the distribution of mass in galaxies and test theories of dark matter and modified gravity in real time. Another area where technology is making a significant impact is the development of computational models. These models simulate the dynamics of galaxies, including the distribution of visible and dark matter, and help us to predict the behavior of galaxy rotation curves under various conditions. The use of supercomputers to run these simulations has given us deeper insights into the interplay between gravity, dark matter, and galaxy structure. By comparing the outcomes of these simulations with actual observational data, scientists can refine their models and develop a more comprehensive understanding of galaxy dynamics. These simulations are particularly important because they allow astronomers to test the effects of different types of dark matter, including whether it is a cold or warm form of dark matter. Cold dark matter, which is made up of slow-moving particles, is currently the leading candidate, and most models assume it to be the primary contributor to the rotation curves of galaxies. However, alternative forms of dark matter, such as warm dark matter or even self-interacting dark matter, could potentially alter the dynamics of galaxies in ways that we have yet to fully explore. By running simulations with different assumptions, scientists are beginning to understand how these alternative forms of dark matter could affect the rotation curves of galaxies. On the other hand, while dark matter remains the leading explanation for galaxy rotation anomalies, scientists have not ruled out other possible explanations. Theoretical models like modified gravity, MOND, which posits a change in the laws of gravity at large distances, continue to spark debate. MOND's proponents argue that the observed discrepancies in galaxy rotation curves can be explained without invoking dark matter by modifying Newton's laws of gravity in low acceleration regimes. While MOND has had some success in explaining certain observations, it has struggled to account for all the complexities seen in galaxy rotation curves, especially in larger galaxies and galaxy clusters. A particularly interesting feature of the ongoing debate about galaxy rotation curves is how it connects with other cosmological phenomena. For example, galaxy clusters, which are massive groups of galaxies bound together by gravity, also show evidence of anomalous rotation curves. These clusters often exhibit much more mass than can be accounted for by the visible matter within them, suggesting the presence of vast amounts of dark matter. By studying the rotation curves of galaxies within these clusters, we can gain further insights into how dark matter behaves on even larger scales. The findings from such studies could potentially help solve the larger cosmic puzzle of how dark matter interacts with normal matter in these densely packed environments. Furthermore, the study of galaxy rotation curves can also inform our understanding of the early universe. Galaxies have evolved over billions of years, and their rotation curves are a product of that evolution. Observing the rotation curves of galaxies at various stages of their formation and growth allows us to trace their development over cosmic time. The properties of dark matter, the distribution of gas, and the role of galaxy mergers all contribute to the rotation curves we observe today. By studying these aspects in combination, we can build a more complete picture of how galaxies form and evolve, potentially shedding light on the processes that govern the earliest stages of the universe. One particularly intriguing line of inquiry is the connection between galaxy rotation curves and the so-called baryon catastrophe. In the early universe, shortly after the Big Bang, the universe was dominated by a hot, dense plasma of protons, neutrons, and electrons. As the universe cooled and matter began to condense, the first galaxies started to form. The question then arises, how do the visible baryonic matter, such as stars and gas, and the invisible dark matter interact during galaxy formation? In the standard model of cosmology, known as lambda-CDM, cold dark matter with a cosmological constant, dark matter provides the gravitational backbone around which visible matter condenses. However, the distribution of visible and dark matter within galaxies is not as simple as this model suggests. Understanding how baryonic and dark matter interact in the formation of galaxies can offer deeper insights into galaxy evolution and the role of dark matter in shaping the universe's structure. In addition to the evolution of individual galaxies, the study of rotation curves also connects with larger-scale cosmic structures, such as cosmic voids and the cosmic web. The large-scale structure of the universe is often described as a vast network of filaments, clusters, and voids. These structures are shaped by the distribution of dark matter, which acts as the scaffolding for galaxy formation. Understanding how galaxy rotation curves fit into this larger framework of the universe allows scientists to place individual galaxies in a cosmological context. By studying how galaxies interact with one another through their rotation curves, we can begin to piece together how large-scale structures are formed and evolve. Another avenue of investigation in galaxy rotation curves involves the role of gas dynamics. Gas is a crucial component of galaxies, and its behavior can significantly influence the rotation curve. For example, gas clouds can act as tracers of the gravitational potential of a galaxy, providing important clues about the mass distribution within the galaxy. The interplay between gas, stars, and dark matter in shaping the rotation curve is a complex and evolving area of research. Observations of gas and galaxies, particularly through radio and X-ray telescopes, are providing valuable insights into how gas is distributed and how it interacts with other components of the galaxy. These observations are essential for understanding how galaxies grow and evolve over time, as well as how dark matter contributes to their overall structure. Moreover, it is worth considering the relationship between galaxy rotation curves and galaxy morphology. Galaxies come in a variety of shapes, from spiral galaxies with well-defined rotation curves to elliptical galaxies, which tend to have more complex velocity profiles. The differences in rotation curves across various types of galaxies offer insights into their formation and evolution. For example, spiral galaxies tend to have more pronounced dark matter halos, whereas elliptical galaxies, which are typically older and less active, may have different distributions of dark matter. Understanding the variations in rotation curves across different types of galaxies can help us build a more comprehensive theory of galaxy formation. Galaxy rotation curves are one of the most powerful tools available for understanding the structure and evolution of galaxies. They provide crucial information about the distribution of dark matter, the nature of gravity, and the processes that govern galaxy formation and growth. As technology advances, and new observational data continues to pour in, we are likely to uncover even more mysteries hidden within these curves. Whether through the lens of dark matter, modified gravity theories, or the dynamic interplay between gas, stars, and dark matter, the study of galaxy rotation curves will continue to be one of the most exciting and important areas of astrophysical research. And as we learn more about the galaxies in our universe, we will also gain deeper insights into the fundamental nature of the universe itself. The study of galaxy rotation curves is intrinsically tied to some of the most profound questions in cosmology. With every new discovery, we find ourselves peeling back layers of the universe's deep mysteries. One of the questions that keeps scientists up at night is how galaxies manage to form and hold together despite the apparent lack of visible matter to account for their gravitational effects. This is where the idea of dark matter comes in. It's an invisible, mysterious substance that doesn't interact with light in any way, yet its gravitational pull is what's believed to be holding galaxies together and explaining their peculiar rotation curves. Dark matter is thought to make up around 27% of the universe's total mass energy content. Its mysterious properties, including its lack of interaction with electromagnetic forces, meaning it doesn't emit, absorb, or reflect light, make it incredibly difficult to detect directly. In fact, scientists have never been able to observe dark matter through traditional means. Instead, we infer its existence by studying the effects it has on visible matter, especially in galaxy rotation curves. These curves, which show how the speed of stars and gas changes as they orbit the center of a galaxy, provide the most compelling evidence for dark matter. In the past, astronomers believed that the gravitational pull of the visible matter in a galaxy, its stars, gas, and dust, was enough to explain its rotation curve. However, when they began to measure the speeds at which stars and galaxies were rotating, they found something puzzling. The outer stars were moving much faster than they should be, based on the amount of visible matter present. According to Newtonian physics, stars on the outskirts of galaxies should be moving more slowly than those near the center because the gravitational pull from the visible matter would be weaker at greater distances. But that's not what the data showed. Instead, the outer stars were moving at a constant speed, even in the far reaches of galaxies. This discrepancy could not be explained by the presence of visible matter alone. In fact, the rotation curves of galaxies suggested that they had far more mass than what was visible. This led scientists to propose that there must be some unseen, or dark, matter in the outskirts of galaxies, exerting gravitational forces and preventing the outer stars from flying off into space. This was the birth of the dark matter hypothesis. The idea of dark matter was first proposed in the 1930s by the Swiss astronomer Fritz Zwicky, who was studying the Coma galaxy cluster. Zwicky noticed that the galaxies within the cluster were moving much faster than expected, based on the visible mass of the cluster. He suggested that there must be some additional unseen mass holding the galaxies together. His idea was met with skepticism at the time, but as observational technology advanced, the evidence for dark matter grew stronger, especially through the study of galaxy rotation curves. As astronomers and physicists dove deeper into this issue, the question arose, what exactly is dark matter made of? Currently, the leading theory is that dark matter consists of particles that don't interact with light but interact with each other through gravity and possibly the weak nuclear force. Several candidates have been proposed, with the most widely discussed being weakly interacting massive particles, WIMPs. These hypothetical particles are thought to be much heavier than ordinary matter particles, and they would interact very weakly with regular matter, making them nearly impossible to detect directly. Despite extensive research, WIMPs have yet to be detected, and alternative dark matter candidates, like axions or sterile neutrinos, are also being investigated. Beyond just proposing the existence of dark matter, the study of galaxy rotation curves has also opened up questions about the nature of gravity itself. The famous flatness of galaxy rotation curves, where the speed of stars remains constant despite the distance from the galactic center, has led to debates about whether or not our understanding of gravity is incomplete. One alternative explanation to dark matter is the idea that gravity behaves differently at large scales or in low acceleration environments. This is the premise behind modified Newtonian dynamics, MOND, a theory proposed by Mordechai Milgram in the 1980s. MOND suggests that Newton's laws of motion and gravity, which work well on small scales, break down in the low acceleration regime of large galaxies. According to MOND, the discrepancy in galaxy rotation curves is due to a modification of gravitational forces rather than the presence of dark matter. While MOND has had some success in explaining galaxy rotation curves, it faces challenges in explaining other cosmic phenomena, such as the cosmic microwave background radiation or the large-scale structure of the universe, which are better explained by the presence of dark matter. As a result, while MOND remains a topic of active research, most cosmologists still favor the dark matter hypothesis, although the debate continues to fuel important discussions about the fundamental nature of gravity and the universe. Another important aspect of galaxy rotation curves is their relationship with the formation of galaxy clusters. When galaxies collide or merge, their rotation curves can change, sometimes dramatically. These mergers can cause the galaxies to lose their spiral structure, resulting in elliptical galaxies, which are thought to be more common in dense galaxy clusters. The interaction between galaxies can also cause the dark matter halos around these galaxies to interact in unexpected ways, influencing the overall rotation curves of the merging systems. In fact, some of the most striking evidence for dark matter comes from observations of galaxy clusters, where the separation between the visible matter and the gravitational mass inferred from lensing effects provides strong indications of dark matter. One of the most exciting developments in the study of galaxy rotation curves is the use of gravitational lensing to map dark matter. Gravitational lensing occurs when a massive object, such as a galaxy cluster, bends the light from objects behind it due to its strong gravitational field. By studying how light is bent as it passes through these massive objects, astronomers can map the distribution of dark matter in and around galaxy clusters. This technique has provided some of the most direct evidence for the existence of dark matter, revealing large, diffuse halos of dark matter surrounding galaxies and galaxy clusters. In some cases, gravitational lensing has even allowed scientists to map the distribution of dark matter with more precision than ever before. The study of galaxy rotation curves has not only advanced our understanding of the cosmos but has also led to new technologies and observational techniques that are reshaping the field of astronomy. One example is the development of radio telescopes like the Square Kilometre Array, SK, which is designed to be the largest and most sensitive radio telescope ever built. The SK will allow scientists to observe galaxy rotation curves in far greater detail than ever before, enabling them to test dark matter theories and explore the physics of galaxy formation with unprecedented precision. Another exciting avenue of research is the use of multi-wavelength astronomy. By studying galaxies across a wide range of electromagnetic wavelengths, from radio waves to X-rays, astronomers can gain a more complete picture of galaxy dynamics. For example,
Observing the gas in galaxies through radio telescopes can provide valuable insights into how the gas interacts with dark matter and stars. Similarly, X-ray observations of galaxy clusters can reveal the behavior of hot gas and dark matter in the largest structures of the universe. As we continue to probe the mysteries of galaxy rotation curves, the future of this research looks incredibly promising. With new technologies on the horizon, such as next-generation space telescopes and more sensitive instruments on Earth, we will be able to test our current theories and uncover new ones. Perhaps most exciting of all is the potential for new breakthroughs that could revolutionize our understanding of the universe. Will we finally detect dark matter particles directly? Will we find evidence for a new form of gravity that could explain the anomalies in galaxy rotation curves? The answers to these questions could change the way we think about the universe and our place within it. As our understanding of galaxy rotation curves deepens, the implications of these findings stretch far beyond just understanding galaxies themselves. The way in which galaxies rotate is closely tied to larger cosmic structures, from galaxy clusters to the entire observable universe. In fact, the study of these rotational anomalies has become an essential pillar of cosmology, influencing theories on the formation and evolution of the universe itself. One of the most profound consequences of studying galaxy rotation curves is the impact it has had on our understanding of the universe's composition. The invisible force that dark matter is thought to exert on galaxies is so strong that it significantly affects the rate at which galaxies form and evolve. In the earliest stages of the universe, after the Big Bang, matter clumped together due to gravity, eventually forming galaxies. However, without the presence of dark matter, these structures would likely have been far less stable, leading to a less varied and much smaller universe. The rotation curves of galaxies suggest that dark matter is crucial not just for maintaining the balance of individual galaxies, but for allowing the formation of larger cosmic structures. Moreover, these findings have pushed scientists to reevaluate our understanding of galaxy formation. Early models of galaxy formation suggested that gas and dust would collapse inwards under gravity, forming stars and galaxies. But if dark matter wasn't included in the equation, the expected speed of stars at the outer edges of galaxies would be much slower than what we observe. This mismatch between theory and observation led to the dark matter hypothesis, which posits that unseen mass in the form of dark matter provides the necessary gravitational support to hold galaxies together, especially in their outer regions. As a result, galaxy formation models have been increasingly integrated with dark matter simulations, which are becoming more sophisticated every year. These simulations allow scientists to create highly detailed, three-dimensional models of galaxies and their surrounding dark matter halos. By comparing these simulations to real-world data, astronomers can better understand how galaxies form, evolve, and interact with one another over time. These simulations have not only confirmed the need for dark matter in galaxy rotation curves, but they have also provided insight into the processes that govern galactic mergers, star formation, and the role of supermassive black holes at the center of many galaxies. Another intriguing aspect of galaxy rotation curves is the fact that they appear to be universally consistent across a variety of galaxies, even though galaxies come in all shapes and sizes. Whether we're looking at a small dwarf galaxy or a massive spiral like the Milky Way, galaxy rotation curves tend to exhibit a similar flatness in their outer regions. This uniformity has led scientists to question whether this behavior is a consequence of the laws of physics, or if there's something deeper at play. Some researchers have even proposed that this consistency could provide clues to understanding the nature of dark matter itself. For example, one hypothesis is that dark matter might not consist of particles at all, but could be something more exotic, such as a form of dark energy, or some unknown field that affects gravity on large scales. If this were true, it would challenge much of what we currently know about particle physics and force us to rethink fundamental concepts like mass, gravity, and the very structure of spacetime. This remains a speculative area of research, but the idea that dark matter could be a manifestation of some yet-to-be-understood force is a tantalizing prospect for those hoping to push the boundaries of modern physics. At the same time, the study of galaxy rotation curves has led to groundbreaking discoveries in other areas of astrophysics. For example, galaxy rotation curves have provided important evidence for the existence of supermassive black holes. These black holes, often found at the centers of large galaxies, have a profound influence on the motion of stars and gas in their immediate vicinity. By studying the rotation curves of galaxies near the centers, scientists have been able to infer the presence of these black holes and study their properties. This is crucial because understanding the dynamics of supermassive black holes can help us better understand the processes that govern galaxy formation and evolution. In addition to studying the motion of stars and gas within galaxies, astronomers have also turned their attention to the intergalactic medium, the gas and plasma that exists between galaxies. The presence of dark matter and its effects on galaxy rotation curves could also influence the behavior of this diffuse gas. Some researchers believe that the gravitational influence of dark matter could play a role in the formation of large-scale cosmic structures, such as galaxy clusters, which are the most massive gravitationally bound objects in the universe. By studying galaxy rotation curves and the distribution of dark matter, scientists are beginning to map out the intricate web of cosmic structure that stretches across the entire universe. In fact, dark matter is thought to be a key ingredient in the creation of the cosmic web, the vast network of interconnected galaxies, galaxy clusters, and filaments that make up the large-scale structure of the universe. These structures are thought to have formed as a result of gravitational collapse, with dark matter playing a central role in providing the necessary gravitational scaffolding. Understanding how dark matter influences the rotation curves of individual galaxies is thus not just important for understanding galaxy dynamics, but also for understanding the larger-scale structure of the universe. One of the most exciting developments in recent years is the advancement of observational techniques that allow us to study galaxy rotation curves with even greater precision. For example, the advent of extremely sensitive radio telescopes has allowed scientists to map the gas and dust in galaxies with unprecedented detail. This has led to more accurate measurements of galaxy rotation curves, helping to refine our understanding of dark matter and its role in galaxy dynamics. Additionally, new techniques in gravitational lensing are allowing astronomers to measure the distribution of dark matter in galaxy clusters with unprecedented precision, providing further confirmation of the dark matter hypothesis. As technology continues to improve, astronomers will be able to observe the rotation curves of galaxies across the entire universe. These observations will not only help us refine our models of galaxy formation and evolution, but they will also shed light on some of the most fundamental questions in astrophysics. For example, by studying the rotation curves of distant galaxies, scientists hope to gain insight into the early stages of galaxy formation and the role that dark matter played in the development of the first galaxies after the Big Bang. This could help answer some of the most profound questions about the origins of the universe and the nature of the forces that shaped it. Furthermore, future space missions like the James Webb Space Telescope, JWST, and the upcoming European Space Agency's Euclid mission are set to revolutionize our ability to study galaxy rotation curves. These missions will allow scientists to observe galaxies in infrared and other wavelengths, providing new insights into the distribution of dark matter and the behavior of galaxies on the largest scales. With the ability to observe galaxies billions of light-years away, these telescopes will help us peer deeper into the universe's past and unlock the secrets of galaxy formation and evolution. The study of galaxy rotation curves has transformed our understanding of the universe. It has provided strong evidence for the existence of dark matter, led to the development of new theories about galaxy formation, and influenced our understanding of the large-scale structure of the universe. While many questions remain unanswered, the discoveries made so far have reshaped the field of cosmology and opened up new avenues of research that promise to push the boundaries of human knowledge. As technology continues to advance, our ability to probe the mysteries of galaxy rotation curves will only increase, bringing us closer to uncovering the deepest secrets of the cosmos. As we continue to probe deeper into the universe, the implications of galaxy rotation curves extend into even more complex and profound realms of scientific inquiry. The study of these curves does more than just validate the existence of dark matter,
It opens the door to understanding the fundamental forces that govern the cosmos and challenges our perception of the very fabric of reality. Every new observation, every new calculation, is a step toward revealing not only the nature of galaxies themselves but also the deep, hidden mechanisms that drive their formation and evolution. One of the key questions that has emerged from the study of galaxy rotation curves is the behavior of dark matter on scales larger than individual galaxies. While the presence of dark matter has been well established in the context of galaxy dynamics, there are still major questions regarding how dark matter interacts on cosmic scales. For example, dark matter is believed to form large halos around galaxies, but the exact shape, distribution, and density of these halos remain subjects of ongoing investigation. The rotation curves of galaxies offer a unique tool for studying these halos and understanding their role in the larger scale structure of the universe. Some researchers have proposed that dark matter might not only be distributed in halos around galaxies, but could also be present in a more diffuse form across the entire universe. This idea, known as the cosmic web, suggests that dark matter could be distributed in long filaments, stretching across vast distances between galaxies and clusters of galaxies. The rotation curves of galaxies, when studied in the context of these larger structures, could provide crucial insights into the distribution of dark matter on a cosmic scale, helping to refine our understanding of the universe's architecture. Another intriguing possibility is that the behavior of galaxy rotation curves could reveal more about the interaction between dark matter and ordinary matter. In the standard model of cosmology, dark matter is thought to interact only via gravity, but there are alternative theories that propose interactions between dark matter and other forces. For example, some models suggest that dark matter might interact with itself in ways that could affect the distribution of mass within galaxies. If such interactions are present, they could have a profound impact on the shape and behavior of galaxy rotation curves, leading to new insights into the fundamental properties of dark matter. At the heart of these questions lies the role of gravity. Our current understanding of gravity, based on Einstein's theory of general relativity, has been highly successful in explaining many aspects of cosmic phenomena, including the rotation curves of galaxies. However, the observation that galaxies rotate much faster than predicted has led some to propose that our understanding of gravity might need to be revised. While dark matter is the leading explanation, alternative theories such as modified Newtonian dynamics, (MOND), have been proposed. MOND suggests that gravity behaves differently at extremely large scales, which might explain the flatness of galaxy rotation curves without the need for dark matter. While MOND remains a minority viewpoint, the fact that it continues to be discussed is a testament to the mystery surrounding galaxy rotation curves and the potential for new breakthroughs in physics. The implications of these findings are not just theoretical. Understanding the true nature of dark matter and the behavior of galaxy rotation curves could have practical applications as well. For example, new theories about the distribution of dark matter might help refine our understanding of gravitational lensing, a phenomenon where the light from distant objects is bent by the gravity of intervening objects. Gravitational lensing has become an essential tool for studying distant galaxies, and improving our understanding of how dark matter influences this process could lead to more precise measurements of cosmic distances, the distribution of galaxies, and the structure of the universe. Additionally, the exploration of galaxy rotation curves has significant implications for the search for habitable planets and extraterrestrial life. By studying the distribution of dark matter in galaxies, astronomers can learn more about the conditions necessary for the formation of stable, habitable environments. Dark matter influences the distribution of mass in galaxies, and in turn, affects the formation of stars and planetary systems. If dark matter has an impact on the rate of star formation or the stability of planetary orbits, it could play a role in the conditions that make life possible. Understanding the relationship between dark matter, galaxy dynamics, and the formation of habitable planets is an exciting frontier in the search for life beyond Earth. As we continue to explore the mysteries of galaxy rotation curves, it's important to remember that these observations represent only the tip of the iceberg. While we have made tremendous strides in understanding the behavior of galaxies, much of the dark matter that influences these curves remains invisible to our instruments.
The study of galaxy rotation curves is therefore part of a larger effort to detect and understand dark matter in all its forms. For example, experiments such as the Large Hadron Collider and various underground detectors are searching for direct evidence of dark matter particles, which could provide crucial insight into the nature of dark matter and its role in galaxy dynamics. Furthermore, the study of galaxy rotation curves has sparked a renewed interest in the possibility of new, exotic forms of matter and energy that could be present in the universe. Some theories suggest that dark matter might be composed of previously unknown particles or fields that interact with ordinary matter in ways we have yet to detect. These ideas have led to new proposals for experiments and observations that could uncover new physics, potentially leading to a revolution in our understanding of the universe. On a more speculative level, some researchers have suggested that understanding the behavior of galaxy rotation curves could help solve some of the most profound mysteries of physics. For example, by understanding how dark matter interacts with ordinary matter, scientists may be able to gain insights into the unification of the fundamental forces of nature. The search for a theory of everything, which would unite gravity, electromagnetism, the strong nuclear force, and the weak nuclear force into a single framework, could benefit from the discoveries made in the study of galaxy rotation curves and dark matter. If new forms of matter and energy are discovered, they could provide the missing link between the known and unknown forces that govern the universe. The study of galaxy rotation curves is a journey that has only just begun. While we have made tremendous progress in understanding the fundamental forces that govern the behavior of galaxies, the mysteries of dark matter, gravity, and the large-scale structure of the universe are far from solved. As new technologies and observational techniques continue to emerge, we are poised to make even more exciting discoveries. Each new observation brings us one step closer to unraveling the secrets of the cosmos, and the study of galaxy rotation curves will undoubtedly remain at the forefront of this quest for knowledge. The next few decades promise to be an exciting time for cosmology, as we push the boundaries of our understanding and explore the mysteries of dark matter, galaxy formation, and the universe itself. The answers we find could fundamentally alter our understanding of the cosmos and our place within it, opening new avenues of discovery that we can barely begin to imagine. What we are witnessing today is not just the unraveling of the secrets of galaxy rotation curves, but the beginning of a new era in our exploration of the universe. As we continue to venture deeper into the universe's secrets, one of the most exciting aspects of the study of galaxy rotation curves is the way it is reshaping our very understanding of how galaxies evolve and interact. These curves, initially thought to merely highlight a discrepancy in the gravitational behavior of galaxies, have evolved into a vital tool for understanding the cosmic scale. They help us see not just the gravitational influence of dark matter, but also the intricate, dynamic processes that take place within galaxies. For instance, the way galaxies interact with each other, whether through mergers or gravitational interactions, can significantly influence the observed rotation curves. Galaxy mergers, for example, are one of the most profound events in the life of a galaxy. When two galaxies collide, their stars rarely interact directly because the vast distances between them make stellar collisions incredibly unlikely. However, the gravitational effects of these collisions are immense. The rotation curves of the resulting galaxies may shift significantly due to the redistribution of dark matter, gas, and stars during these interactions. These mergers also play a crucial role in galaxy formation and evolution, influencing the way galaxies cluster together over cosmic time. The effects of galaxy mergers are observed in the kinematic data, which show changes in the velocity distributions of stars and gas. In some cases, these interactions lead to the creation of elliptical galaxies, where the rotation curves are more random due to the disruption of the original galactic structure. In other cases, they might lead to the formation of irregular galaxies or fuel-active galactic nuclei, where supermassive black holes at the center of galaxies become active and release enormous amounts of energy. These galactic interactions raise an interesting question. If galaxy rotation curves are influenced by these events, could there be additional unknown forces or phenomena at play? The potential for unexpected behaviors in these systems is huge.
Could the dynamics of galaxy rotation curves reveal interactions between visible and dark matter that we hadn't considered? Could there be forces beyond dark matter, hidden in the interplay between galaxies, that influence the rotational behavior we observe? Each new data point presents more possibilities and pushes the boundaries of our understanding further. This brings us to the evolving role of simulation in our exploration of galaxy rotation curves. Modern computational techniques have allowed astronomers and physicists to simulate galaxy dynamics with unprecedented detail, providing insights into how galaxies form, evolve, and interact under the influence of dark matter and other unseen forces. These simulations can model everything from the gas dynamics to the behavior of stars, helping scientists predict what the rotation curves of various types of galaxies might look like. Through these simulations, we can test theories about dark matter and gravity, seeing if they hold up against observed data. Interestingly, these simulations also help identify the limits of our current models. While they have been invaluable in explaining the rotation curves of galaxies, there are still many anomalies that challenge these models. Some galaxies exhibit rotation curves that are not easily explained by the standard theories of dark matter. For example, in certain low-mass galaxies, the rotation curves appear to flatten in a way that is inconsistent with the dark matter halos we expect. This has led to further refinements in our models, suggesting that there may be nuances to dark matter that we haven't yet captured. Perhaps dark matter interacts differently in certain environments, or is distributed in ways we hadn't previously imagined. Moreover, the continued study of galaxy rotation curves is pushing the boundaries of observational technology. As we develop more advanced telescopes, such as the James Webb Space Telescope, we gain the ability to look further and deeper into space, examining the rotation curves of galaxies that are billions of light-years away. This allows us to study galaxies in the early universe and investigate how their rotation curves evolved over cosmic time. This could potentially reveal how galaxies formed and evolved in different cosmic epochs, offering critical insights into the behavior of dark matter in the early universe. The role of galaxy rotation curves is especially critical when we consider the cosmic scale. Dark matter is thought to account for a significant portion of the universe's mass, yet it remains largely invisible to our instruments. Understanding its distribution within galaxies gives us a glimpse into the large-scale structure of the cosmos. It helps us see how galaxies are linked together, forming clusters and superclusters, connected by vast cosmic filaments made of dark matter. The study of galaxy rotation curves, therefore, provides us with a key to understanding the broader architecture of the universe. It tells us how galaxies are arranged in space and how the gravitational pull of dark matter influences their motion. In addition to this, the dynamics of galaxy rotation curves also provide valuable information about the age of galaxies and the processes that drive their evolution. By analyzing how rotation curves change over time, astronomers can learn about the life cycles of galaxies, from their formation to their eventual end. For example, the growth of a galaxy's dark matter halo over time can be used to estimate the galaxy's age, while the movement of stars and gas within the galaxy can provide clues about the processes that govern star formation. This process not only enhances our understanding of individual galaxies but also offers a broader perspective on the life cycle of the universe itself. With all of this in mind, it's clear that the study of galaxy rotation curves is not merely an academic exercise. It's a crucial piece of the puzzle in understanding the universe. These curves tell us more than just the rotational speed of stars in a galaxy. They reveal the hidden forces that shape the universe, from the invisible dark matter that surrounds galaxies to the complex interactions between galaxies. Each new discovery about galaxy rotation curves is like a new chapter in the story of the universe, one that is far from over. The future of galaxy rotation curve research is incredibly exciting. As technology advances, we will gain more detailed and accurate data, enabling us to test more theories and refine our models. Whether we are looking at galaxies up close, observing them in distant corners of the universe, or simulating their behavior with advanced computational tools, we are on the brink of a new era of discovery. There is much left to uncover about the hidden structures of galaxies and the mysterious role of dark matter in shaping the universe. As we continue this journey, the mysteries of galaxy rotation curves will undoubtedly play a pivotal role in our quest to understand the cosmos. As we move forward in this exploration of galaxy rotation curves, it's important to consider how they continue to challenge and refine our understanding of physics itself. While dark matter is the leading explanation for the anomalies observed in galaxy rotation curves, it's crucial to remember that this is still a theory. There are alternative hypotheses that seek to explain these observations, and some of them present equally fascinating possibilities. One such alternative is modified Newtonian dynamics, MON. Proposed by physicist Mordechai Milgram in the 1980s, MON suggests that Newton's laws of motion and gravitation may need to be modified at very low accelerations. According to MON, the observed flatness of galaxy rotation curves is not due to the presence of dark matter but rather to a modification of gravity itself. This theory challenges the standard cosmological model that heavily relies on dark matter as the primary explanation for galactic dynamics. MOND has had some success in explaining certain galaxy rotation curves, particularly in low-mass galaxies, where the discrepancy between the expected and observed velocities is especially noticeable. In these cases, the theory predicts a much flatter rotation curve than what would be expected from the visible matter alone. However, MOND has yet to be universally accepted because it struggles to explain phenomena at larger scales, such as the behavior of galaxy clusters and the cosmic microwave background radiation. Another intriguing avenue of research is the potential connection between galaxy rotation curves and the geometry of spacetime itself. Some researchers have proposed that the effects we attribute to dark matter might instead be a result of warped spacetime on a cosmic scale. This approach would involve a deeper understanding of general relativity and its implications on large-scale structures, offering a potential new way to view the universe's dynamics. The complexity of general relativity, however, makes this an especially challenging hypothesis to test, requiring not just observational evidence but a comprehensive rethinking of how we model the gravitational interactions that shape galaxies. The observational challenge of studying galaxy rotation curves extends beyond merely interpreting the data. It also involves the precision with which we can gather information. Observing the rotation curves of distant galaxies often involves measuring the Doppler shifts of light emitted by stars and gas clouds within those galaxies. The accuracy of these measurements is crucial, as small errors can lead to vastly different interpretations. Instruments like the Very Large Telescope, VLT, in Chile or the Atacama Large Millimeter/Submillimeter Array, ALMA, in the desert of northern Chile are essential for obtaining high-resolution data on galaxy rotation. These instruments have revolutionized our ability to probe the dynamics of galaxies across vast distances, providing more accurate velocity profiles and offering a clearer picture of galactic motion. Additionally, the advent of new technologies, such as the upcoming James Webb Space Telescope, JWST, promises to take this research even further. The JWST will allow us to observe galaxies in infrared wavelengths, which will be invaluable for studying older, distant galaxies that are obscured in visible light. The ability to peer into the deeper universe and obtain more detailed observations of galaxy rotation curves will undoubtedly lead to breakthroughs in our understanding of how galaxies form, evolve, and behave over time. By observing galaxies as they were in the early stages of the universe, we can also gain insights into how dark matter and ordinary matter interacted in the distant past. But even as technology advances, there are still fundamental questions that remain unanswered. How does dark matter behave on the smallest scales within galaxies? Is it distributed uniformly, or does it have clumps that could explain the peculiarities observed in certain rotation curves? We know that dark matter interacts with itself gravitationally, but does it have any other properties that we haven't yet detected? Could dark matter have more complex dynamics than we realize, possibly interacting with itself in ways that affect the formation of galaxies and their rotational behavior? On the other side of the spectrum, our understanding of the visible matter in galaxies is also evolving. The gas that forms stars and the stars themselves play a significant role in the rotational motion we observe. It's becoming clear that the way stars and gas are distributed within galaxies can affect their rotation curves. For example, the concentration of stars in the center of a galaxy, or the way gas clouds interact with the galactic disk, can lead to variations in the rotational velocity profiles. These interactions add layers of complexity to the models used to explain galaxy rotation curves. And as our observations improve, we are starting to uncover more about how these interactions contribute to the overall dynamics. One of the most fascinating aspects of galaxy rotation curves is the role of the so-called dark halo, the invisible envelope of dark matter that is believed to surround every galaxy. This dark halo is thought to be responsible for the flatness of the rotation curves observed in the outer regions of galaxies. However, the precise nature of these halos remains elusive. What shape do they have? Are they spherical, or do they take on more complex forms due to interactions with other galaxies? These questions are at the cutting edge of research in galaxy dynamics. As we continue to push the boundaries of our understanding, the study of galaxy rotation curves opens up broader questions about the fundamental structure of the universe. How do galaxies form, and how does dark matter fit into this picture? What is the ultimate fate of these galaxies, and how does their rotational behavior reflect their history and future? These are questions that are not only of academic interest but have profound implications for our understanding of the cosmos. The interplay between visible matter, dark matter, and gravity remains one of the most fundamental mysteries in modern astrophysics. As researchers continue to study galaxy rotation curves, they are not just investigating the motion of stars and gas, they are probing the very nature of the universe itself. Each new discovery brings us one step closer to understanding the unseen forces that govern the cosmos, and each new piece of the puzzle adds to our growing picture of the universe's grand design. The study of galaxy rotation curves has evolved into one of the most exciting and dynamic areas of astrophysical research. From dark matter to galaxy mergers, from modified gravity theories to cutting-edge observational techniques, there is still so much to uncover. The rotation curves of galaxies offer us a unique window into the workings of the universe, revealing not just the nature of dark matter but also the fundamental forces that shape galaxies and the cosmos at large. As technology advances and our understanding deepens, the mysteries of galaxy rotation curves will undoubtedly continue to captivate and challenge scientists, pushing the boundaries of what we know about the universe. The journey to unravel these cosmic mysteries is far from over. In fact, we are only beginning to scratch the surface of what is possible. Who knows what new revelations await us in the coming years as we push the limits of both our observational capabilities and our theoretical models? One thing is for certain, the study of galaxy rotation curves will continue to be at the forefront of our quest to understand the deepest workings of the universe. As we continue to explore the intricacies of galaxy rotation curves, it's important to keep in mind that the journey to understand these phenomena is not just about uncovering dark matter or tweaking the laws of gravity. It's about expanding the scope of our knowledge and pushing the boundaries of human understanding. Every new insight into the dynamics of galaxies has the potential to reshape our comprehension of the universe itself. To further enrich our grasp of galaxy rotation curves, it's essential to discuss some of the ongoing challenges in this field, particularly the complexity of galaxy formation and the role of galaxy interactions. The first of these challenges is the variability in galaxy rotation curves across different types of galaxies. While spiral galaxies, for instance, tend to show remarkably consistent flat rotation curves, the same cannot be said for irregular galaxies, dwarf galaxies, or elliptical galaxies. Each galaxy type appears to have unique characteristics that influence how it rotates, and this variability has posed difficulties in creating a unified model that explains all galaxies uniformly. For example, the rotation curves of elliptical galaxies, which are generally more compact and do not have the prominent disk structure found in spiral galaxies, often behave differently. In these galaxies, the velocity profiles do not always flatten out in the same manner as they do in spiral galaxies. This has led researchers to hypothesize that the distribution of dark matter in elliptical galaxies might differ from that in spiral galaxies, possibly taking on a more spherical or even anisotropic distribution. This raises intriguing questions about how galaxy morphology, the shape and structure of a galaxy, might influence the behavior of dark matter and consequently, the galaxy's rotation curve. Dwarf galaxies present another puzzle. These small galaxies are of particular interest because their rotation curves often exhibit steep rises at the inner regions, followed by flatness at larger distances. However, some dwarf galaxies deviate from this expected behavior, showing either a lack of a flat rotation curve or a more complex, irregular profile. The underlying reasons for this are still not entirely understood, but it suggests that there may be additional factors at play, such as interactions with other galaxies or unique properties of the dark matter halos surrounding these galaxies. Some dwarf galaxies are also observed to contain a relatively low amount of visible matter, making the role of dark matter even more critical in understanding their rotation curves. The role of galaxy interactions, particularly mergers and tidal forces, cannot be overstated. When galaxies collide and merge, the dynamics of their rotation curves are often altered in dramatic ways. These interactions can trigger starbursts, disrupt the distribution of both visible and dark matter, and lead to complex changes in the overall rotation pattern. In some cases, galaxy mergers have been shown to induce the formation of new stellar populations, with subsequent changes in the distribution of mass within the galaxy. These mass redistributions are critical in shaping the galaxy's rotation curve, and in some cases, they may obscure the typical signature of dark matter. When studying galaxy mergers, one might observe that the rotation curves of the resulting galaxies often become distorted, showing velocity patterns that don't correspond to the classical models. These distortions could provide important clues about the behavior of dark matter in extreme environments. It's possible that these collisions cause the dark matter to be distributed differently within the merged galaxy, leading to new structures within the galactic halo, or a different relationship between visible and dark matter in the galaxy's outer regions. These complex galaxy interactions and their resulting rotation curves also emphasize the need for advanced simulations in astrophysics. Over the past few decades, the development of sophisticated computer simulations has become essential in modeling galaxy formation, structure, and evolution. Through these simulations, scientists can replicate the effects of galaxy mergers, tidal forces, and dark matter distribution in virtual environments, providing insights into how galaxies evolve and how their rotation curves behave over time. These simulations also allow researchers to test different hypotheses about dark matter, modified gravity theories, and other variables that could influence galaxy dynamics. What's remarkable about these simulations is their ability to compare theoretical predictions with real observational data. By analyzing the outcomes of simulations and comparing them to the velocity profiles we observe in real galaxies, researchers can refine their models and test which variables have the most significant impact on galaxy rotation curves. For example, a simulation may predict that a certain distribution of dark matter results in a rotation curve similar to those observed in spiral galaxies. If real data matches this simulation, it strengthens the case for the existence and specific distribution of dark matter. Conversely, if the data does not match, it could suggest that modifications to gravity or other aspects of our understanding need to be reconsidered. One of the most exciting aspects of this field is the ongoing refinement of observational techniques. The more accurate and detailed our measurements become, the more we can uncover about the nature of galaxies and their rotation curves. The next generation of telescopes and observational instruments promises to make a significant impact in this area. In particular, the upcoming launch of next-generation radio and space telescopes will provide insights into regions of space that are currently beyond our reach. Radio telescopes, like the Square Kilometre Array, SKA, will allow scientists to observe galaxies in unprecedented detail by detecting low-frequency radio waves emitted by the cold hydrogen gas that constitutes much of a galaxy's mass. By examining the rotation of this gas, scientists can gain a better understanding of how galaxies rotate, especially in the outer regions where dark matter is thought to dominate. The SKA will enable us to observe galaxies in various stages of evolution, including those far beyond the Milky Way, and thus, we will be able to compare rotation curves across a much broader spectrum of galaxy types, redshifts, and environments. In addition to radio observations, the launch of the James Webb Space Telescope, JWST, would provide high-resolution infrared imaging and spectroscopic data. These capabilities will allow astronomers to peer deeper into galaxies, even those located in the distant universe. Since infrared light can pass through the dust that often obscures other wavelengths, the JWST will give us clearer views of the central regions of galaxies, where the rotation curves are influenced by the distribution of stars, gas, and dark matter. The data from the JWST could help resolve some of the lingering questions about galaxy rotation curves, particularly in understanding how they vary across cosmic time. As these technologies advance, the data we gather will undoubtedly lead to new insights about the role of dark matter, the nature of galaxy formation, and the forces that govern the dynamics of galaxies. The results will likely challenge our current theories and models, prompting new questions about how the universe works at its most fundamental level. In the larger context, the study of galaxy rotation curves has far-reaching implications for cosmology and the understanding of the universe's evolution. The shape and behavior of rotation curves give us clues not just about the distribution of matter within galaxies, but also about the large-scale structure of the universe. For example, the behavior of galaxy clusters and the way they interact can provide insights into how matter is distributed across vast cosmic distances. The study of rotation curves, particularly when combined with observations of cosmic structures like galaxy clusters and the cosmic microwave background, can help refine our models of the universe's birth and evolution, shedding light on the underlying forces that shape the cosmos. One of the ultimate questions at the heart of this research is the nature of dark matter itself. While we have strong evidence for its existence, dark matter remains one of the most elusive substances in the universe. It does not emit, absorb, or reflect light, making it invisible to our most powerful telescopes. Yet, its presence is inferred from its gravitational effects on visible matter. The fact that dark matter is responsible for shaping the rotation curves of galaxies raises profound questions about its true nature. Is it made up of exotic particles, such as weakly interacting massive particles, WIMPs, or does it involve more complicated phenomena, such as axions or sterile neutrinos? These questions remain at the forefront of research, with scientists around the world racing to uncover the elusive nature of dark matter. The investigation of galaxy rotation curves may very well hold the key to answering these questions. By continuing to gather more detailed observational data and refining our theoretical models, we may one day be able to reveal the true nature of dark matter and unlock the secrets of the universe's most mysterious substance. Until then, the study of galaxy rotation curves will continue to be an exciting and ever-evolving area of astrophysical research, with each new discovery offering tantalizing clues about the fundamental forces that govern the cosmos. Dwarf galaxies are of particular interest because their rotation curves often exhibit steep rises at the inner regions, followed by flatness at larger distances. However, these flat regions tend to manifest at much lower velocities compared to larger spiral galaxies, and they sometimes show unexpected features like sudden drops or irregular wiggles that challenge theoretical modeling. Since dwarf galaxies are often heavily dominated by dark matter relative to their visible matter, they serve as excellent testing grounds for both the dark matter hypothesis and alternative theories like MOND. Yet, interpreting the data is far from straightforward. The observational data from dwarf galaxies can be significantly influenced by small-scale astrophysical processes. Feedback from intense star formation can drive powerful outflows of gas, which in turn alter the distribution of mass and energy in the galaxy. This feedback can change the gravitational potential and skew the rotation curve. Additionally, many dwarf galaxies reside in dense environments where they are subject to tidal stripping, gravitational forces from nearby galaxies or clusters that tear away gas and stars from their outskirts. These interactions can dramatically reshape the rotation curves, masking or mimicking the effects we typically attribute to dark matter or modified gravity. These complexities have led astronomers to refine their simulations and models in attempts to account for such influences. High-resolution simulations now incorporate feedback effects, baryonic physics, and cosmic environment factors to more accurately reproduce the observed rotation curves. Interestingly, some simulations have begun to match the rotation curve data better than ever before, yet discrepancies still persist, especially in the outer regions of galaxies where the gravitational pull from visible matter is expected to be weakest. This discrepancy remains a central mystery, Why do the outer regions of galaxies not show the expected decline in velocity as predicted by Newtonian dynamics? Instead of tapering off, the velocities remain flat, or in some cases, even rise slightly. This is where the dark matter hypothesis continues to dominate the conversation. The most commonly accepted explanation is that an unseen halo of dark matter extends well beyond the visible components of the galaxy, providing the extra gravitational pull necessary to maintain those flat rotation curves. But the shape, composition, and interaction of this dark matter halo remain elusive. Theoretical physicists have proposed several dark matter models to explain these observations. The most traditional one is cold dark matter (CDM), where dark matter is made up of slow-moving, weakly interacting particles that clump together under gravity. CDM has had enormous success at explaining large-scale structures in the universe, such as the cosmic web and galaxy clusters. However, at the scale of individual galaxies, CDM struggles with certain phenomena like the cusp core problem. This refers to the discrepancy between the steep density peaks, cusps, predicted by CDM in the centers of galaxies and the flat, core-like distributions observed in real galaxies. To address this, some researchers have proposed warm dark matter, WDM, which consists of slightly faster-moving particles. WDM may smooth out the density peaks, offering a better fit for observed core structures. Others have taken this even further by suggesting self-interacting dark matter, SIDM, where dark matter particles interact with each other through a new force that only affects the dark sector. These interactions could allow dark matter to redistribute itself in the inner regions of galaxies, smoothing out the density profile and potentially matching observations more closely. Beyond particle-based theories, there are also radical proposals that dark matter may not be composed of particles at all. Concepts like scalar field dark matter or wave dark matter involve treating dark matter as a quantum field with wave-like properties. These models introduce interference patterns and quantum pressure that could help explain some of the peculiarities in rotation curves, especially in low-mass galaxies where quantum effects become more significant. While still highly speculative, these theories show how deeply the rotation curve problem has penetrated into the frontier of fundamental physics. And yet, the mystery doesn't stop at individual galaxies. When astronomers analyze rotation curves across thousands of galaxies, they notice something even more astonishing: a universal scaling relation. This relation, often described in terms of the baryonic Tully-Fisher relation (BTFR), shows a tight correlation between the total baryonic mass of a galaxy and the asymptotic flat velocity of its rotation curve. The fact that this relation holds across such a wide range of galaxy types, sizes, and environments is both surprising and telling. It suggests an underlying rule or mechanism guiding the structure of galaxies that we do not yet fully comprehend. The BTFR poses a significant challenge to both dark matter and modified gravity theories. For dark matter models, this tight correlation demands a very specific and finely tuned coupling between baryonic and dark matter distributions, a coupling that doesn't naturally arise from basic gravitational dynamics alone. For modified gravity theories like MOND, the BTFR emerges more naturally, which gives them a potential edge in this regard. However, MOND still faces major hurdles in explaining galaxy clusters, gravitational lensing, and cosmological data without invoking some form of unseen matter. Even more confounding are recent observations of ultra-diffuse galaxies (UDGs). These are large galaxies with very low surface brightness, often containing relatively few stars spread out over enormous areas. Some of these galaxies appear to be missing large amounts of dark matter, while others seem to be dark matter heavy. This inconsistency raises serious questions about our current models. If dark matter is a universal component of galaxies, why do some UDGs seem to defy this rule entirely? Could it be that certain galactic processes expel or redistribute dark matter in ways we don't yet understand? Or could this point to a more fundamental gap in our understanding of gravity itself? Adding to the complexity, there is also the issue of rotational asymmetry. Not all galaxies rotate in a clean, symmetric fashion. Many show signs of lopsidedness, warps, or other kinematic irregularities that are difficult to reconcile with simple models. These asymmetries can arise from past interactions with nearby galaxies, internal instabilities, or even mergers. But they may also signal a deeper layer of complexity in the gravitational dynamics of galaxies. As we move forward, the key to unlocking the mystery of galaxy rotation curves may lie in combining observational precision, theoretical innovation, and computational power. The next generation of telescopes, such as the Vera C. Rubin Observatory, the James Webb Space Telescope, and the Square Kilometre Array, are poised to provide incredibly detailed rotation curve data for galaxies across the observable universe. With this data, astronomers hope to probe deeper into the outskirts of galaxies, where the influence of dark matter or modified gravity should be most pronounced. Meanwhile, theoretical physicists are pushing the limits of current models, exploring new forms of matter, dimensions, and interactions. The interplay between observation and theory will be critical in determining whether dark matter truly exists as a particle, or whether our understanding of gravity needs to be rewritten. Whichever path we follow, one thing is clear: galaxy rotation curves have become one of the most profound probes of fundamental physics available to us. The outer regions of galaxies rotate at speeds that suggest the presence of far more mass than what is visible through telescopes. According to Newtonian mechanics and general relativity, the rotational velocity of stars and gas in a galaxy should gradually decrease with distance from the galactic center, similar to how planets in our solar system orbit more slowly the farther they are from the Sun. However, observations consistently show that the rotation curves of galaxies remain flat, or even rise slightly in these outer regions, defying expectations based solely on luminous matter. This persistent flatness implies the existence of an additional gravitational force, one that does not correspond to any visible mass. The most widely accepted explanation for this phenomenon is the presence of dark matter, a form of matter that does not emit, absorb, or reflect light, making it invisible to conventional astronomical instruments. Dark matter is thought to form an extended halo around galaxies, accounting for the gravitational effects needed to sustain the observed rotational speeds. The concept of a dark matter halo is central to modern cosmology. These halos are believed to extend well beyond the visible boundaries of galaxies, encompassing and influencing the motion of stars and interstellar gas. In fact, the size of a typical dark matter halo can be several times larger than the luminous portion of a galaxy. While we cannot observe these halos directly, their effects are inferred from gravitational lensing, galaxy rotation curves, and the large-scale structure of the universe. Despite the success of the dark matter paradigm in explaining many cosmic phenomena, its nature remains one of the most profound mysteries in physics. Numerous candidates have been proposed to account for dark matter, ranging from weakly interacting massive particles, WIMPs, to axions and sterile neutrinos. Each of these candidates comes with its own theoretical framework and experimental challenges. WIMPs, for instance, are hypothetical particles that interact through the weak nuclear force and gravity but not through electromagnetism, which would explain their invisibility. Their mass and interaction properties could potentially allow them to be detected in underground laboratories or through high-energy collisions and particle accelerators. However, decades of experiments have yet to yield definitive evidence of WIMPs, leading some researchers to question whether dark matter consists of an entirely different kind of particle, or if it exists at all. Axions are another proposed candidate. These ultralight particles were initially introduced to resolve a different problem in quantum chromodynamics, but they also possess properties that make them suitable as dark matter candidates. Axions would be nearly invisible to detectors but might produce detectable signals through their interactions with magnetic fields, inspiring ongoing searches using resonant cavities and other sensitive instruments. Sterile neutrinos, yet another possibility, are theorized to interact only through gravity and not via any of the standard forces of the standard model of particle physics. If they exist, these particles could contribute to the mass needed to explain galaxy rotation curves and might be detectable through their decay signatures in cosmic radiation. All of these dark matter candidates are part of an intense global effort to uncover the true nature of the unseen mass that shapes our universe. Particle physics, cosmology, and astronomy have become increasingly intertwined as researchers collaborate across disciplines to solve this riddle. Experiments such as the Large Hadron Collider, the Xenon Dark Matter Experiment, and the Axion Dark Matter Experiment represent just a few examples of humanity's ongoing attempts to detect these elusive particles directly. Beyond particles, some theories explore the idea that our understanding of gravity itself might need revision. General relativity, though incredibly successful in explaining a wide range of phenomena, might break down at galactic or cosmological scales. This possibility has led to the development of alternative theories of gravity, many of which attempt to explain the galaxy rotation curve anomalies without invoking dark matter. Among these, modified Newtonian dynamics, MOND, remains the most studied and discussed. MOND suggests that at very low accelerations, on the order of meters per second squared, gravity behaves differently than predicted by Newton's law. Under this regime, the gravitational attraction between masses weakens more slowly than expected, leading to higher rotational velocities at large distances from the galactic center. This adjustment in the laws of motion can reproduce flat rotation curves without requiring dark matter. Although MOND has enjoyed success in explaining the rotation curves of many galaxies, it struggles when confronted with phenomena on larger scales, such as the dynamics of galaxy clusters and the behavior of the early universe. To address these shortcomings, more comprehensive frameworks like TeVis, tensor, vector, scalar gravity, have been proposed. These models attempt to blend the core ideas of MOND with relativistic theory, making them compatible with general relativity and potentially consistent with cosmological observations. Nevertheless, none of these alternative gravity theories have achieved the same broad applicability as the dark matter hypothesis. They often require fine-tuning or additional assumptions that reduce their elegance and predictive power. Still, their continued development is a testament to the creativity and persistence of scientists who refuse to accept unsolved mysteries without a thorough investigation of all possible explanations. The rotation curves of galaxies are not only a window into the nature of dark matter or gravity, they are also a record of each galaxy's unique history. Galaxies evolve over billions of years, undergoing collisions, mergers, and internal transformations that shape their structure and dynamics. These processes can leave lasting imprints on their rotation curves, creating irregularities, asymmetries, and deviations from the norm. For instance, galaxies that have experienced recent mergers often display disturbed rotation curves. The gravitational turmoil of the merger process can redistribute stars, gas, and dark matter, leading to temporary anomalies in the velocity profile. Some galaxies exhibit counter-rotating disks or warps in their outer regions, features that are best explained by the accretion of material from other galaxies or the influence of nearby companions. Environmental effects also play a critical role. Galaxies in dense clusters are subjected to tidal forces, high-speed interactions, and gas stripping due to the intracluster medium. These forces can dramatically alter the distribution of mass and angular momentum, leading to observable changes in rotation curves. Even isolated galaxies can experience internal processes, such as the formation of bars or spiral arms, that redistribute mass and angular momentum over time. Understanding these environmental and evolutionary factors is crucial for interpreting rotation curve data accurately. Without accounting for them, researchers risk attributing observed anomalies to exotic physics when they may instead arise from more mundane astrophysical processes. Advanced simulations that include both dark matter dynamics and baryonic physics have become essential tools in disentangling these effects. As computational power grows and observational instruments become more sophisticated, our ability to map and analyze galaxy rotation curves improves dramatically. Surveys like the Sloan Digital Sky Survey (SDSS), the HI Nearby Galaxy Survey (THINGS), and the upcoming Vera C. Rubin Observatory's Legacy Survey of Space and Time (LSST) promise to deliver unprecedented volumes of high-resolution data on galaxy dynamics. These surveys not only increase the statistical power of rotation curve studies but also allow researchers to explore trends across different types of galaxies, environments, and cosmic epochs. They enable comparative studies that can reveal whether the anomalies observed are universal features of galactic dynamics or contingent on specific conditions. The stakes are high. If the dark matter hypothesis is correct, then its confirmation will revolutionize particle physics and offer new avenues for exploring the fundamental structure of the universe. If, however, gravity itself is different from what we believe, then our understanding of space, time, and the cosmos may require a profound transformation. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.